Currently, hovering roughly 19 million miles over Mars, an anomaly is streaking through space that defies all logic. Not in this location. Not at a blistering 210,000 kilometers per hour. Not venting gases like a comet, yet hardly nudged by its own exhaust streams. Dubbed 3I Atlas, the third verified interloper from beyond our solar system. This enigma is reaching its nearest point to the red planet this evening, and every probe we've got in orbit is locked on it. Opinions are divided among the bold few willing to speculate. 60% chalk it up to nature, while 40% hesitate to dismiss the possibility of intelligent design. The composition is off-kilter. It's spewing carbon dioxide at 8 times the pace of water vapor, a proportion so odd it deviates 6 standard deviations from the norm. Dimensions are a mystery too, with projections spanning 300 meters to 5 kilometers. Plus, the odds of spotting an entity this enormous as merely our third extrasolar find leave experts uneasy. 3 theories swirl around this fleeting guest. Data pouring in tonight might resolve the debate or amplify the weirdness. What are the Mars satellites capturing as this intruder races by? What glimpses will Hubble snag at perihelion 3 weeks from now? And if the figures refuse to align post-flyby, how does that upend our grasp of the universe? Before we unpack the real action unfolding above, smash that subscribe button and drop in the comments where you're tuning in from this evening. Share your take too. Do you believe we're the sole spectators, or is another intelligence out there observing alongside us? Kicking off with part 1, the close encounter set to rattle the globe. This very night, October 3rd, 2025, even as these words reach you, and relic from distant stars is hurtling beyond Mars at more than 210,000 kilometers per hour. We call it 3I Atlas, and it's poised to brush nearer to the rusty world than any of us might come to decoding its true nature. Dozens of Mars-orbiting missions have their sensors zeroed in on this outsider, and rightfully so. This goes beyond your typical comet. It's the third authenticated interstellar body to traverse our cosmic backyard in human records, acting in manners that unsettle scientists to their core. Let me lay out the backstory. Back in 2017, an oddity named Oumuamua whipped across our turf, sparking universal bewilderment. It sped up in defiance of comet norms. Shaped like a cigar or a flapjack, take your pick, it slipped away before telescopes could probe deeper. Fast forward to 2019 and 2I/Borisov arrived, a welcome return to sanity. It resembled a classic comet, behaved accordingly, sported a crisp envelope of fumes and particles, and let stargazers rest easy. The cosmos clicked back into place. We all exhaled in unison. That illusion shattered on July 1st, 2025. The Atlas Survey, our frontline alert network for potential doomsayers or head-scratchers, picked up a fresh anomaly. Something zipping unnaturally. Not faulty, but utterly alien to our realm. Its path was hyperbolic, unbound by Sol's pull. It originated from the void between stars and is merely transiting. Hence, 3I Atlas earned its tag. The I flags interstellar, since we've apparently hit the era demanding protocols for extraterrestrial drop-ins. Now, the intrigue ramps up. Hubble scans cap the core at about 5.6 kilometers wide. That's no small fry. To put it in perspective, it's on par with the impactor that doomed the dinosaurs. Yet, the twist, it might be way tinier. Guesses dip as low as 320 to 440 meters. Quite the uncertainty range. The culprit? The nucleus hides behind a hazy sheath of vapors and debris, bloating its profile. Thus, we're navigating in the dark, a shaky spot when discerning organic from engineered. But scale's not the sole riddle. Enter non-gravitational propulsion. As comets warm under solar glare, they eject volatiles, which act like mini-jets steering their course. It's faint, yet detectable. Oumuamua showed this boost without a visible haze, fueling whispers of artificial origins for some. Conversely, 3I Atlas boasts a vivid, hyperactive envelope. JWST has clocked its furious emissions, but the extra push is faint to the point of irrelevance. The motion implies a bare minimum heft of 33 billion tons and a span of at least 5 kilometers, per JWST's emission data. That's dense. Incredibly so for an object potentially shy of 6 kilometers. The equations clash. And in astrophysics, When numbers rebel, wild ideas emerge. This evening, 3i Atlas is sweeping within 18 to 19 million miles FR. Picture this. The distance to Mars right now is about 29 to 30 million kilometers, if you're into metrics. Come December, it'll swing by Earth at its nearest point, roughly 269 million kilometers away. To put it plainly, our homeworld faces absolutely no danger from this. Zip. Nada. Yet this close shave with Mars is a golden opportunity to examine the visitor in detail. Several probes are circling the red planet, equipped with cutting-edge gear, and they're all tuned in. Think of it as a stellar flyby where we're parked in the prime viewing spot. The composition is downright intriguing on its own. Observations from the James Webb Space Telescope revealed a haze mostly made of carbon dioxide, with a CO2 to H2O proportion around 8:1. That's one of the highest ratios recorded for any comet in history. Typically, these icy wanderers are loaded with water. Frozen H2O drives most of the activity. But not this one. It's spewing CO2 as if it's attempting to reverse engineer Mars' atmosphere. Alongside the carbon dioxide, detectors picked up water vapor, carbon monoxide, carbonyl sulfide, and even ice grains from water. Still, the proportions feel off-kilter. It's reminiscent of spotting a creature that looks, sounds, and acts like a duck, yet turns out to have the flavor of steak. Feasible in theory, but it demands a thorough review of the classification. Enter Avi Loeb. If you're not in the loop, he's a Harvard astrophysicist who's built a sideline exploring the chance that certain visitors from beyond our system could be engineered. He floated the idea of a light sail accounting for Oumuamua's odd speed-up. Though many peers aren't buying it, he's now focusing on 3i/Atlas. He's devised what's known as the Loeb scale, a 0 to 10 gauge for assessing if an object might be alien tech. 0 signals purely natural origins. 10 indicates verified extraterrestrial craft, potentially hazardous. Back in early August, reports pegged 3i/Atlas at a 6 on that scale. That's suggesting a 60% shot at it being tech-made. In a follow-up Medium article, as fresh info rolled in, Loeb dialed it back to 4 out of 10. Elevated enough to keep the door open, yet tempered. Regardless of whether you buy into his method, that score has sparked a raging discussion. So here we are, with Mars-based probes scanning this enigma through the night via their instruments. 3 main theories vie for attention. 1. The standard take. It's a comet, an oddball one, with quirky makeup, but just a stellar drifter from afar. 2. The relic idea. This could be constructed, dispatched intentionally, maybe even observing us while we scrutinize it. 3. A blend that's somehow milder yet scarier. Imagine it's a piece of wreckage from a long-gone catastrophe, shattered light years from any sun, drifting in a trail we're only now crossing paths with. If the surrounding cloud is genuine venting, how come the thrust from those emissions is so feeble? Why the lopsided mix of elements? Why at this moment? Why 3 such intruders in just 8 years, after eons of sky gazing? As 3i/Atlas zips by Mars tonight, we could uncover some truths, or end up with sharper puzzles. Part 2. Insights from Mars, the quiet observers. Time to dive into the action unfolding overhead at this very moment. The European Space Agency's got 2 orbiters around Mars ideally placed for the rendezvous. There's Mars Express, probing the rusty world since 2003, and the more recent ExoMars Trace Gas Orbiter, which lifted off in 2016. They're both set to track 3i/Atlas from October 1st to 7th, peaking in alignment today, October 3rd. And this setup isn't mere chance. Mars Path offers a stellar observation post. Here's the reason. Tracking an interloper hurtling at cosmic speeds demands varied perspectives. Earth gives us a single angle on 3i/Atlas. From Mars, sitting some 225 million kilometers distant, give or take, based on orbital positions, we snag a fresh outlook. It's akin to viewing a vehicle speeding down the road from street level versus from an aerial drone. Such positioning uncovers details a lone vantage misses, like the haze's shape, any jets, spin patterns. With viewpoints scattered across vast space, these traits sharpen into focus. What precisely are these Martian satellites aiming to capture? Let's simplify without needing a doctorate. Start with spectroscopy, splitting light into its colors to spot gases in the envelope. Each compound soaks up and gives off light at unique bands. Analyzing those tells us what's sublimating from the core. JWST handled the infrared side earlier, highlighting that strange CO2 prevalence. The Mars tools will verify if that pattern persists or shifts as the body navigates varying warmth zones. One key way to probe this interstellar visitor is through its apparent size. Ground-based telescopes and Hubble can gauge the object's dimensions by how much light it scatters, though the surrounding haze from the coma often blurs things. A larger body could point to a chunkier asteroid-like form, while something tinier might resemble a comet nucleus or even dust ball. Next up is its reflectivity, or albedo, which reveals the fraction of incoming sunlight bounced back versus soaked up. Something super dim could be loaded with carbon-rich stuff, packed with organics akin to a charred s'more drifting in the void. On the flip side, a shinier one might be frosted over, untouched and fresh. That albedo hints at what's on the surface, and if cosmic rays have baked the materials for eons while cruising between stars. Another angle is the periodic dips in brightness from rotation. If it's flipping or whirling, the light we see will pulse as various sides face our way. The rhythm of those pulses, captured in the light curve, spills details on its form. Is it round, stretched out, or all wonky? Crucially, does it spin steadily and smoothly, or tumble wildly like it's recovering from a rough hit? Then there's the coma's outline. Material doesn't just vent evenly from a comet. You get targeted bursts, geysers of stuff shooting from spots where ice lies bare or pressure builds below. JWST has already noted the coma's lopsided form. Mars spacecraft can follow how that imbalance shifts with varying sun angles. Natural jets ought to react straightforwardly to solar warmth. If they don't, that's intriguing territory. Finally, watch the outbursts in activity. Comets sometimes flare up abruptly when sealed volatiles burst free, sparked by heat cracks, spin stresses, or tiny collisions. Tracking these spikes, or their absence, uncovers clues about the guts inside. But catch this snag. Even at peak closeness tonight, 3I Atlas remains absurdly distant from Mars for fine observing. Think tens of millions of kilometers. The thing might span just a handful of kilometers, maybe less, all wrapped in a wispy coma. It's dim, zipping by quick, and the Mars probes have tight schedules since they're tuned for the red planet, not flyby guests. So an absence of detection doesn't rule out features. The signal could be too faint or the window missed. That's why blending viewpoints matters hugely. Hubble delivers sharp detail, teasing the core from the nearby gas better than most tools. JWST uncovers chemical signatures, with its IR tech picking up gas molecules' unique traits exquisitely. Mars orbiters track shape shifts over quick intervals. Merge them, and you tighten the theories. Toss a hypothesis that matches Hubble's scale but clashes with JWST's makeup, or one that nails JWST's CO2 levels yet forecasts a coma form at odds with Mars Express views. That's suspect too. Science thrives on cross-checking, and we're building a solid setup here. So what might oddities show up as? Picture a bizarre pulse rhythm that defies basic spinning, maybe a jagged, intricate form, naturally quirky but worth a closer look. Or a sideways burst not aligned with sun-driven heat, hinting at hidden layers below. For the adventurous mind, perhaps deliberate steering or light shifts ignoring solar input. Normal glow varies with sunlight. Unrelated ups and downs beg questions. There's buzz too about NASA's Mars Reconnaissance Orbiter possibly snapping shots via its HiRISE imager, a beast for crisp planetary views. But let's tread lightly. No firm word yet on assigning HiRISE to this. It's feasible, even smart for the science payoff, but without official nod, it's just potential. Keep an eye out. Peering farther, JUICE enters the scene, a mission folks overlook for now. Launched in 2023, it's bound for Jupiter to eye the frozen satellites, but its current spot offers a fresh vantage. Down the line in 3I Atlas's path, JUICE might provide extended views from another solar system corner. Such spread-out snapshots across days or weeks lock in paths and spot faint tweaks. Still, temper hopes. Initial pics or readings from the Mars flyby could lag days or weeks. Data flows raw from the probes, then undergoes calibration. Data undergoes careful filtering to strip away instrumental noise. It's refined further to boost the signal-to-noise ratio. Research groups document their findings. Colleagues scrutinize it, or at minimum, the team conducts internal checks. Eventually, it might hit publication or appear online as a preliminary version. That's standard procedure. That's simply how scientific inquiry operates. Nothing nefarious about it, just thorough and deliberate. So, if you're anticipating some dramatic announcement at dawn with irrefutable proof either supporting or debunking theories, dial back those expectations. In time, we'll likely gain a sharper view of what 3i Atlas is up to during this pivotal phase of its path. And that insight will lead straight into the follow-up puzzle. What's the true composition of this enigma? Part 3. Dissecting 3i Atlas. Time to explore the tangible makeup of this entity, based on our current, admittedly limited, grasp. The scale range is annoyingly broad. Hubble's data caps the core at roughly 5.6 kilometers in width. Yet, given the vigorous and luminous haze surrounding it, the real core might be considerably tinier. Certain projections dip down to 320 to 440 meters. That's a 10-fold gap in width, which balloons to a 1,000-fold spread in overall bulk. In a detective story, we describe the culprit as ranging from 5 feet 2 inches to 6 feet 8 inches. Hardly a precise sketch. The cause of this vagueness is simple enough. The core itself isn't visible. Instead, we're observing reflected starlight bouncing from vapor and debris in the envelope, with the nucleus tucked away amid that radiance. It's akin to spotting a stone beneath a churning, silt-filled stream. Physics insists it's present, but direct sizing proves elusive. Now, things turn truly intriguing. A fresh study on its motion crunches orbital data with remarkable accuracy, drawing from position logs worldwide, hobbyist scopes, pro setups, the works. Monitoring an object across months and modeling its path against those observations reveals faint strays from pure gravity's pull. Such anomalies, those extra forces beyond gravity, reveal the thrust from vapor release. For 3i Atlas, it's around 3 times 10 carat, minus 10 astronomical units per day squared. A minuscule value, really. By contrast, most lively comets exhibit non-gravity boosts many magnitudes greater. But the riddle emerges here. Armed with that force and the emission levels from JWST data, you can reverse engineer the bare minimum weight. The figures indicate at least 33 billion tons. Factoring in a plausible density for comet-like stuff, say 500 kilograms per cubic meter, that suggests a span of no less than 5 kilometers. Spot the alignment? It hugs the top of Hubble's boundary. Thus, either it's truly that bulky and hefty, or the premises in the weight calculation are off base. Perhaps the emissions aren't as uniform as the simulations predict, or the makeup's layout renders the thrust oddly feeble. Or, uncomfortably, it might not be a comet whatsoever. Let's dive into the makeup, since that's where 3i Atlas truly diverges. On August 6, 2025, JWST's NIR spec tool scanned the envelope and clocked a carbon dioxide to water proportion of roughly 8:1. For perspective, comets from our solar system, viewed at comparable solar distances, usually feature water as the main gas, often overwhelmingly so. A standard mix might hover near 1 part CO2 to 10 or 20 parts water. 3i Atlas inverts it entirely, yielding 8-fold more CO2 than H2O. Besides the CO2 and water, traces showed up of carbon monoxide, carbonyl sulfide, and icy water particles. The full mix is present, yet the balances are odd. What might explain this? One angle points to its origins. In a young star system's disk, temps fall with distance from the central sun, and varied frosts solidify at varied ranges. Water frost emerges nearer in. CO2 and CO frosts arise farther, in chillier zones. Should 3i Atlas have coalesced close to the CO2 frost boundary in its home system, it could inherently favor CO2 over water. A solid, organic rationale. Another option involves radiant exposure. Picture this body wandering interstellar voids for eons, pelted by cosmic rays and UV from far-off suns. Such bombardment reshapes outer layers, snapping bonds and forging fresh molecules. It might also form a shielding layer that locks away friskier stuff below. If that shell holds water frost tighter while letting CO2 vent freer, you'd end up with the lopsided release pattern observed. Once more, a plausible organic cause. This interstellar visitor stands out as truly peculiar. Its path is crystal clear. A hyperbolic trajectory indicates it's exceeding the solar system's escape velocity, with no closed orbit in sight. Originating from beyond our stellar neighborhood, it's arcing around the Sun before venturing back into the void. The perihelion, its nearest approach to the Sun, occurs near October 30th, 2025, at roughly 1 for Australian dollars. Positioned just beyond Earth's path, nearer to the Sun than Mars yet farther than Venus, it will face peak solar warmth there. Thus, any striking shifts in its behavior or unusual outbursts are most likely to appear at that moment. Let's highlight the velocity once more. About 210,000 kilometers per hour, or roughly 130,000 miles per hour, equating to around 58 kilometers per second. To put it in perspective, Voyager 1, humanity's quickest spacecraft departing the solar system, travels at just 17 kilometers per second relative to the Sun. 3I Atlas outpaces it by over 3 times. This brisk pace stems from its original interstellar wanderings augmented by the Sun's gravitational pull. Combined with its steep orbital tilt, it irrefutably shows this entity isn't a local product. Now, contrast this with standard comet patterns. Within our solar system, even those long-period visitors from the Oort cloud typically display pronounced water content during activation. The CO2-to-water ratio usually rises only far from the Sun, where water ice remains too frigid to vaporize readily, while more reactive CO2 can still escape. Yet, 3I Atlas activates fairly near the Sun and holds onto that odd proportion. It deviates sharply from the usual curve, sitting about 6 standard deviations higher than norms. In stats, a 6 sigma event prompts doubts about whether the data even belongs to the same group. It's an extreme anomaly even among rarities. Then there's the puzzling slowdown in acceleration. Expelling gases ought to nudge the comet's course. JWST detects abundant venting, yet the observed thrust is negligible. How to explain this? One theory involves counteracting jets. If the core releases material from various spots, and those streams mostly offset each other force-wise, you'd observe vigorous activity with little overall shove. Imagine 4 equally powered rockets blasting from a square formation. The thing would vibrate, but stay put. This scenario makes sense and happens in certain comets, though it demands a precise setup and balance we haven't verified. The other possibility, the body is exceedingly dense, and although the gas release looks striking, it lacks the oomph to budge the path noticeably. Picture using a leaf blower against a massive stone, plenty of wind, scant impact on the obstacle. Should 3I Atlas truly span 5 kilometers with a sturdy core, such emissions might prove too feeble to register any speed up. The math checks out, but it implies this is a heavyweight contender. Spotting a 5 kilometers interstellar interloper so soon in our detection efforts would feel statistically off-kilter. We'll explore that oddity further in the mothership theory discussion. So, what does this reveal about its makeup? We have an entity sizing between 300 meters and 5.6 kilometers wide, enveloped in a lopsided, CO2, heavy coma that's actively evolving. It follows an unmistakable extrasolar route at breakneck pace. Its gas chemistry wildly defies expectations. And amid all this frenzy, its own expulsions barely jostle it. Each observation piles on fresh enigmas rather than resolving them. That escalating oddity is precisely why some speculate we're misjudging the object's true nature altogether. Part 4. The Loeb Scale and the 60% Assessment. Okay, time to tackle the big question staring us down. Avi Loeb, head of Harvard's astronomy department and past leader of the National Academy's Physics and Astronomy Board, has suggested a system to gauge the odds of an interstellar object being artificial. Dubbed the Loeb Scale, it spans 0 to 10. A 0 signals purely natural, be it a stone or comet, with 0 chance of tech roots. A 10 indicates verified alien tech, possibly hazardous. It's patterned after established risk metrics, like the Torino scale for near-Earth objects or the Richter for quakes. The goal: equip scientists, journalists, and everyday folks with a shared way to debate a topic long either ignored or hyped to extremes. Back in early August 2025, Certain public remarks pegged 3i Atlas at a 6 on this scale. That's a 60% likelihood of technological origins. Subsequently, in his Medium articles as fresh details emerged, especially JWST's chemical findings, Low adjusted that assessment to just 4 out of 10, or 40%. Even so, it's notably high, implying a real possibility that this isn't merely a cosmic boulder. Unsurprisingly, this assertion has ignited a fierce divide among astronomers, right through the center. What factors elevate the rating? We'll go over Low's logic step by step. It's thorough, even if it doesn't fully convince everyone. To start, its dimensions are exceptional. If 3i Atlas truly measures 5 kilometers across or more, based on trajectory and mass calculations, that's rare. Typically, the interstellar wanderers we spot tend to be tiny, since smaller items vastly outnumber the giants. Spotting a planet smasher-scale fragment this soon in our observations, after just 2 prior confirmed interstellar guests, strikes Low as statistically unlikely. It's akin to hitting the jackpot on your 3rd try. Feasible, but eyebrow-raising. Next, the faint non-gravitational push amid evident activity. When an object ejects enough stuff to form a detectable coma visible in JWST data, it ought to experience noticeable momentum. Yet the influence remains slight, pointing to either an exceptionally hefty body or a propulsion pattern that's oddly balanced. Low points out that both could occur naturally, yet they align with a massive engineered structure releasing material for purposes beyond simple ice vaporization. Finally, the composition. That 8-to-1 ratio of carbon dioxide to water is strikingly peculiar. Natural origins exist, as we've covered, but for an interstellar craft's engine, you'd select propellants for practicality and longevity, not universal availability. CO2 turns to gas at warmer temps than water ice, potentially simplifying long-term handling over eons in the void. Pure conjecture, of course, but it's the sort of nuance that piques Low's interest. On the flip side, what lowers the rating? Above all, the coma composition. JWST detects straightforward signs of everyday comet volatiles: water, CO2, CO, CS, and icy particles. This matches standard comet reactions. No traces of synthetic chemicals, odd isotopes hinting at lab creation, or sharp signals from tech leaks. The venting follows patterns tied to solar warmth and evaporation, bolstering the organic explanation. Moreover, no obvious adjustments in path. A working vessel would likely show intentional shifts, speed changes defying pure gravity or basic outgassing. Up to now, 3i Atlas's route fits a straightforward hyperbolic arc, gravity with a touch of coma thrust. Nothing indicates guided navigation. Additionally, its entry path doesn't raise red flags. Speculation abounds that an extraterrestrial scout might approach obliquely for secrecy or better views. But 3i Atlas's tilted orbit is standard for outsiders. They originate beyond our disk. The trajectory appears, well, haphazard. So what's the consensus in astronomy? NASA's official statements and announcements label it an interstellar comet, posing zero Earth risk. The tone is measured yet firm. It's deemed natural barring major surprises. The ESA mirrors this view. From what I've seen, most experts weighing in lean toward the comet theory, noting that quirky chemistry doesn't equate to impossibility, especially with only 3 such visitors studied. Basing broad theories on 3 samples is like gauging human stature from a trio of passers-by. You could nail it, but odds are against. Media distortions complicate things further. Sensational sites, chasing views and drama, hype the ET narrative with tales of motherships and armadas. Others dismiss even mild curiosity as fringe nonsense or publicity stunts. The sensible center, likely natural, but worth monitoring, fades away as subtlety sells less than extremes. Regarding balance, science demands robust proof for bold assertions. Carl Sagan popularized that idea, turning it into gospel. Claiming 3i Atlas as alien tech carries a heavy onus of evidence. What kind of proof would seal the deal? Propulsion-style actions that outgassing alone couldn't account for. Radio signals in tight frequency bands that aren't found in nature. Light patterns matching engineered materials. Mirror-like bounces, flashes from panels, angular shapes, heat outputs that defy simple sun-warmed expectations. In essence, you'd want clear indicators shouting, "Made by intelligent hands." Lowe's model aims to measure that level of proof. Rather than a yes or no split between natural and extraterrestrial, it uses a gradual spectrum. The concept involves plotting detected oddities onto a fluid rating. That rating evolves with fresh data. At the start, with sparse details, you might rate it higher due to all the unknowns. But as evidence piles up, especially if it aligns with ordinary explanations, the rating falls. And that's precisely the pattern with 3i Atlas. The original 6 out of 10 stemmed from patchy data. The updated 4 out of 10 factors in JWST's chemical analysis and the absence of any detected propulsion. Should upcoming views reveal steady, foreseeable comet-style motion around perihelion, the rating ought to decline more. Yet there's another dimension to weigh, one that dives into deeper philosophical waters. The spectrum doesn't merely pit natural against man-made. It also weighs risk against harmlessness. Imagine a crafted item that's completely innocuous, a lifeless probe, a broken satellite from a vanished society, or a silent observer with zero agenda toward Earth. On the flip side, picture a natural body like a comet barreling straight at us, pure peril. These dimensions stand apart. Low scale focuses on the odds of it being artificial, but popular chatter often mixes that with peril, sparking those grim dark forest scenarios, which we'll explore down the line. The main point: Lowe's rating serves as a tool for sparking ideas, not delivering judgments. It's like a starting assumption in Bayesian lingo. You begin with a likelihood drawn from current clues, then refine it with incoming info. Many experts today would peg that starting point way below 4 out of 10. Still, the approach itself, the push for a structured method to assess these visitors, makes solid sense. We'll encounter more from beyond our system. The Vera Rubin Observatory, set to activate soon, will spot them at rates vastly exceeding today's hunts. A shared framework for gauging just how bizarre each one is could prove handy. So, does 3i Atlas stand a 60% chance of being alien tech? Hardly. At 40%? Still unlikely. But 0%? That's the query Lowe urges us to ponder earnestly. Love it or dismiss it. That debate fuels the intrigue as telescopes system-wide lock onto this small, speeding zipping by Mars this evening. Up next, we'll break down the science confirming its interstellar origins and the spots where the numbers raise eyebrows. Part 5. The Orbital Enigma. How do we confirm beyond doubt that this visitor hails from outside? It's no simple matter. The cosmos is vast, immensely so, and objects follow intricate paths shaped by layered gravity pulls. Spotting something zipping along doesn't automatically mean it's starborn. You require precise trajectory calculations, and luckily, we've got them. By monitoring an object's path over weeks or months, you amass location readings. Every sighting yields a right ascension and declination at a given moment. Plug sufficient data into trajectory algorithms, and it computes the 6 essentials for an ellipse or hyperbola: semi-major axis, eccentricity, inclination, perihelion argument, ascending node longitude, and perihelion timing. For sun-trapped items, eccentricity stays under 1, an ellipse, looping forever. For interlopers from afar, it's over 1, a hyperbola, open-ended. The visitor entered from the void, loops the sun, and departs to the void anew. 3i Atlas boasts an eccentricity well above 1. No looping orbit fits. This entity was never, and isn't now, tied gravitationally to our star. The hyperbolic surplus speed, the velocity left over after stripping away solar pull, is yet another telltale sign. For 3i Atlas, it's in the range of dozens of kilometers per second. That's its pace through the galactic medium prior to our system's tug. Nothing routine inside the solar system could boost an object to that without a slingshot from a hefty gravifier. And its path skirts clear of any such aid that might justify it. The visitor showed up bearing that velocity wasn't picked up in our solar system. Yet this is where doubts start to emerge. Scientists can track the present path with remarkable accuracy. They can extrapolate rearward to approximate the body's origin. But approximate carries a heavy load there. As time reverses further, the margins for error balloon dramatically. Across eons, small deviations in today's course multiply into vast location ambiguities long ago. Experts are certain that 3I/Atlas hails from beyond our stellar neighborhood, likely originating in the broad vicinity of the constellation it approached from upon discovery. However, zeroing in on a precise stellar home isn't feasible. The Milky Way's motion patterns are intricate. Celestial bodies shift positions. Intruders get nudged by nearby stars. Rewind the trajectory by 1,000,000 years, and the uncertainty span stretches to tens of light years. Push it to 10 million years, and it balloons to hundreds. Beyond that, there's the puzzle of the initial launch. Stars don't casually hurl large-scale items into the void for amusement. An underlying process is required. One candidate involves gravitational deflections from massive planets amid a system's early development. Simulations indicate that nascent planetary setups are turbulent zones, where worlds shift orbits and icy bodies like asteroids and comets get hurled about. A fraction of such debris reaches breakout speed and turns interstellar. Indeed, projections imply billions or even trillions of wandering comets and asteroids may roam our galaxy's gaps today, potentially surpassing the count of stars. A different theory points to near-miss stellar flybys. When two suns cruise within several light years, their pull can yank comets loose from Oort clouds and propel them away. Alternatively, in a bolder case, a sun might be booted from its cluster, towing comet reserves that later shed into the interstellar expanse. Or, and this ties into theories of scattered remnants, some disaster struck. Perhaps a world-smashing impact, or a tidal shredding as a rogue planet neared its sun too closely and tore apart, or a blast from a supernova in the vicinity. Each event could fragment a planet and launch shards outward at tremendous pace. Now, consider the upcoming closest solar approach, set for late October, specifically October 30th, 2025. There, 3I/Atlas will reach its minimum distance from the Sun, around 1.04 astronomical units, comparable to the Earth-Mars gap. Sunlight intensity will peak. For a typical comet, this should trigger heightened gas release. Vaporization rates ought to surge. The surrounding haze would likely glow brighter and perhaps grow. Should the observed non-gravitational push remain modest or fail to scale with the emissions, it bolsters the idea of a dense core. This implies the body carries substantial weight, and even though the gas output dazzles our detectors, it falls short of meaningfully steering its path. Still, perihelion might uncover oddities. Comets often flare unpredictably near the Sun. Abrupt activity jumps that don't align neatly with heat exposure. Such surges might stem from buried volatile reserves erupting suddenly, akin to a safety valve popping on a sealed pot. If 3I/Atlas surges, and that surge yields a detectable path shift, analysts would have to scrutinize if it matches even-sided venting or hints at aimed propulsion implying design. Not claiming we'd spot deliberate control, just that we'd have to exclude it rigorously. Data from JWST on material shedding, paired with motion studies, yields that baseline mass of 33 billion tons. But transparency demands we question the premises in that calculation. It presumes the emissions JWST captured in early August reflect the body's typical output during the orbital analysis window. If activity waxes and wanes unevenly, the weight figure adjusts accordingly. It presumes emissions are mostly balanced or that imbalances cancel out across spins. A steady one-way jet could skew the equations. It also presumes a specific conversion rate from gas expulsion to momentum, influenced by the gas's makeup and ejection velocity. CO2 versus H2O carries varying masses. The blend counts. Thus, the 33 billion ton mark serves as a conservative floor, rooted in particular simulations. It's not a direct gauge like Hubble's dimension cap. It's a deduction, and deductions hold only as firmly as their foundational frameworks. Finally, the rotation and brightness variation issue arises. Pinning down the spin rate and cycle of it by studying the fluctuations in its brightness, we could gain valuable insights into the object's form. A truly round sphere spinning on its axis wouldn't display any changes in light output, but something elongated flipping end over end might alternate between brighter and dimmer phases as varying profiles turn toward us. The extent of those shifts reveals the ratio of its major to minor axis. The timing of the cycles indicates its rotation speed. Capturing this, however, demands frequent photometric monitoring across long stretches of time. Plus, the surrounding coma throws a wrench into it all. What we observe in terms of light is mostly from the coma, overshadowing the core nucleus. Isolating the nucleus's spin signature amid that hazy interference proves incredibly challenging. Upcoming studies could potentially unravel this. Should it eclipse a distant star, the resulting shadow play might yield a precise measure of its dimensions. A radar bounce-back, though a slim chance at such vast distances yet feasible, would supply both scale and rotation details. Once its activity fades markedly after closest solar approach and the nucleus becomes visible, instruments like Hubble or the James Webb Space Telescope could pinpoint its exact measurements. This scenario echoes a notable past event worth recalling. AIR, the initial interstellar interloper, sparked numerous studies attempting to retrace its path. From whence did it originate? Which stellar neighborhood flung it our way? Top analyses, drawing on Gaia archives of star locations and velocities, pinpointed several possible sources, though the margins for error remain enormous. Across the eons that this wanderer, 2I/Borisov, has journeyed, subtle nudges from nearby stars, solar wind pressures, drag from cosmic grains, all these accumulate. The identical issue plagues 2I/Atlas. We can pinpoint its arrival from the void in a broad directional sense. Yet we can't claim it hailed from Tyche 7159 or got booted from the Hyades group. The precision simply falls short. Now, regarding the jet offset effect, it calls for a straightforward breakdown since it's key to aligning the mild thrust with vigorous vapor release. Picture a comet core resembling a spud. Various spots across its skin are venting gases. Should those spots be arranged evenly, and each generate similar propulsion, the overall push on the core might nearly nullify. Think of four folks shoving a vehicle from opposite directions with matching force. The vehicle stays put, merely under strain. This is some unusual dynamics. It's been observed in our own solar system's icy wanderers. Take Comet 67P/Churyumov-Gerasimenko, which Rosetta probed for 2 years. It displayed this precise pattern. Numerous venting zones, intricate streams, yet only moderate deviation from pure gravity owing to mutual jet annulment. Thus, it's feasible for 2I/Atlas, though it demands a particular layout, and it's fair to point out that not every comet shows this trait. Others rely on one dominant plume, leading to pronounced motion boosts. That 2I/Atlas appears to fall into the equilibrated jets group adds yet another entry to the tally of features aligning with typical origins while being a tad offbeat. Don't overlook the collaborative science aspect, which merits applause. The path calculations for 2I/Atlas draw from countless positional readings gathered by global scopes. Pro outfits such as Gemini, Subaru, and the European Southern Observatory contributed, alongside hobbyists using home setups feeding info to the Minor Planet Center. This represents large-scale public involvement. Each sighting sharpens the trajectory, narrows uncertainties, and bolsters predictions. Absent that worldwide web of eyes, our grasp of the object's behavior would be far murkier. So, what does this opening act conclude? The argument for peculiar yet ordinary holds firm. The composition is quirky but accountable. The scale and weight remain vague but viable. The path screams interstellar without doubt. The subdued motion amid robust emissions baffles, but might stem from offsetting streams or hefty bulk. Each oddity offers a credible everyday rationale. Still, the quirks stack up, and though each stands alone as solvable, together they foster an accumulating aura of peculiarity. It's akin to a whodunit where every clue points benignly, but assembled on the board, the arrangement begins to seem shady. The matter isn't settled, it's ajar, with hints of more peeking in. Ahead, let's pit these three ideas against one another and determine which withstands the evidence. Section 6. The Comet Theory, the Cosmos's Quirky Offspring. Begin with the most straightforward account, demanding the least leaps and snugly meshing with established cosmic knowledge. 2I/Atlas is a comet. An interstellar one, indeed. A bizarre comet boasting alien makeup, without question. But at heart, it's a grimy iceball. A fragment of frozen water and stone birthed in a young planetary system orbiting some distant sun, hurled out via orbital tangles, and wandering the Milky Way for millions. It could have wandered through the cosmos for millions or even billions of years before swinging by our cosmic backyard. That's the standard perspective. It's the line NASA pushes in its official releases. It's the go-to answer from most astronomers when pressed on the matter. And this isn't merely due to bureaucratic stubbornness or dismissing other ideas. It's grounded in solid data. The JWST spotted water, carbon dioxide, carbon monoxide, carbonyl sulfide, and icy water particles in the coma. That's exactly the mix you'd anticipate from a comet. These are everyday space volatiles, substances that solidify in chilly interstellar environments and turn to gas when warmed by stellar radiation. The spectral lines line up perfectly with lab-tested profiles for these chemicals. No room for doubt in the IDs. But let's confront the big issue head-on. That bizarre 8-to-1 ratio of carbon dioxide to water. It's truly odd, and it's the wrinkle that stops this theory from being airtight. In our own solar system, we've tracked scores of comets. Most, when they're firing up close to the sun, have water as the main driver of activity. The usual CO2 to H2O proportion is way under 1:1. Often, it's one CO2 molecule for every 10 or 20 water ones. Well-studied cases like C/2019A2 or C/1995-01 Hale-Bopp follow this norm. Even those on the CO2 heavier side seldom top a 1:1 balance. Yet 2I/Atlas is pumping out 8 CO2 molecules per single water one. That's not a minor deviation. It's way out at 6 sigma from the average. In health terms, it's like the gap between mildly high lipids and rushing to the ER. So, an explanation is in order. One idea points to the birthplace conditions. In a young star's disk, temps drop as you venture farther from the central blaze. Near the star, you get scorching, rocky stuff. Push outward, and water frost begins to form. That's the snow line, usually a handful of AU out, varying with the star's brightness. Venture even deeper into the chill, and more fragile ices take shape. CO2 solidifies a tad colder than water ice. CO, super volatile, freezes way farther along. Now, suppose 2I/Atlas originated in a zone of its natal disk cool enough for heaps of CO2 frost, but where water was scarce or bound up in rocky bits. You'd end up with a CO2 dominant makeup right from the start. We see echoes of such gradients here. Kuiper belt bodies vary in ice types based on their formation spots. Some brim with water, others lean toward methane or nitrogen frosts. It's not even across the board. Scale that up to a foreign system, with altered star weight, disk heat gradients, or metal content, and it's easy to imagine setups where CO2 outshines water. Another angle involves radiation wear and tear. Picture 2I/Atlas drifting interstellar voids for 10 million years. All the while, it's pelted by cosmic rays, zippy protons, and atomic bits flung from supernova blasts and cosmic mayhem. Plus, it's soaked in UV glow from far-off suns. This barrage seeps into surface zones, snapping molecular ties. Water can fracture into H and O, CO2 might degrade or morph into fresh forms. Yet the onslaught also builds a protective shell, a crust of altered stuff that's tougher and less prone to vaporizing than the pure ice below. The clever twist here, water and CO2 ices follow distinct vaporization paths. Water ramps up outgassing around 150 to 200 K. CO2 kicks in earlier, below about 150 K. With that crust acting as a buffer, the surface might heat just right to liberate CO2 while trapping water deeper down. You'd get CO2 geysers dominating, despite abundant water in the core. The nucleus acts like a flask with a selective vent, favoring the flightier gas. This setup accounts for the elevated CO2, H2O now, but it forecasts a shift. As solar proximity intensifies and heat drills inward, water should take over. Spotting more water dominance at closest approach would back the crust idea. If the imbalance persists, it points stronger to inherent CO2 wealth. Finally, on the puzzling speed-up issue, the even-thrust jet fix comes into play. It's not as wild as it might seem. Comet cores aren't polished orbs. They're lumpy, with dips, pits, sheer drops, and flat expanses. Some patches bury ice under thick dust blankets. Others expose raw ice or skimpy coverings for easy sublimation. Sunlight striking those lively spots drives gas jets that nudge the whole thing along. Jets burst forth, sweeping up dust in their wake. Every jet generates force akin to a miniature rocket motor. When several jets activate across various spots on the core and their directional forces essentially offset one another, the overall motion remains minimal despite substantial gas output. This concept isn't mere speculation. Rosetta's data from Comet 67P demonstrated it firsthand. That comet featured numerous active zones, with streams shooting from the neck area and the lobes. While some non-gravitational motion was evident, it stayed moderate due to the spread-out jets. 3i/Oumuamua. Wait. No, 3i Atlas. If the uneven envelope spotted by JWST stems from various jets emerging at disparate points on the core, arranged so their sideways forces neutralize each other, but the upward ones shape the visible haze as observed, it perfectly matches what we detect. Intense outbursts, striking envelope, negligible overall shove. The equations hold up, the principles align. It demands a particular configuration, yet comet cores vary wildly in form and scale. It's entirely feasible. Still, let's maintain rigorous scrutiny here. Accepting the minimum mass of 33 billion tons straight up suggests a span of no less than 5 kilometers, based on standard comet densities. That's sizable. The majority of known comets are more compact. Iconic examples like Halley's Comet stretch about 15 kilometers in length, but average roughly 8 kilometers across. Hale-Bopp was gauged at around 60 kilometers. Thus, 5 kilometers is noteworthy yet not unheard of. That said, spotting a 5 kilometers interstellar visitor as merely the third verified ISO raises eyebrows statistically. The bias in detection explains it this way. Our scans favor luminous targets. Luminosity hinges on scale and vigor alike. A petite, highly vigorous comet could outshine a bulky, dormant space rock. Perhaps we're merely glimpsing the surface of the matter, overlooking heaps of tinier, dimmer interstellar wanderers. As detection tech advances, especially with Rubin activating, we'll uncover those lesser bodies, and the size spread will even out. Stumbling on a hefty one so soon is sheer chance, favorable or otherwise, based on your view. The doubters retort that if 5 kilometers ISOs pop up frequently enough to snag one in every 3 finds, the interstellar tally must tilt heavily toward giants, which is tough to justify. Standard theories of solar system buildup forecast that minor fragments should dwarf majors in numbers. The size tally usually adheres to a power law with a sharp decline. Hitting big ones initially is conceivable, but it's the outlier scenario. So, either our theories falter, our datasets too puny for solid inferences, or the items we're picking up are oddly atypical. This leads to how Mars and closest solar approach viewings might validate things. Should jet patterns shift methodically with sun positioning? That's compelling proof of a genuine comet. If the haze's balance alters in tandem with varying light exposure setups, that's the anticipated pattern. If the CO2 to H2O balance tilts more toward water amid rising warmth, it bolsters the idea of a sun-baked outer layer. If we pick up spin cycles matching a wobbling, lopsided core, that's comet territory too. On the flip side, if the outbursts remain oddly steady irrespective of solar input, that's trickier to account for organically. If jet actions ignore sunlight patterns, red flags wave. If luminosity or light spectrum alters without heat as the driver, that's offbeat. One key detail more, zero threat to Earth. 3i Atlas's nearest pass to us hits about 270 million kilometers this December. To put it in perspective, Mars's tightest Earth skim is roughly 55 million kilometers. The Moon sits at about 400,000 kilometers. 3i Atlas poses no impact risk whatsoever. Even supposing it's way bulkier than thought, even if it breaks apart, fragments won't cross our path. This matters because hype around apocalyptic iceballs or alien armadas boosts views but undermines real insight. The danger level is absolute zero, not merely slim. Thus, the comet idea rests on firm footing. Peculiar makeup? Covered. Faint non-gravitational nudge? Accountable via offsetting jets or hefty bulk. Starborne roots? Matches known expulsion processes. Seen haze tied to everyday ices? Verified. Scale and weight ambiguities? not yet dooming the framework. It's the most straightforward take that meshes with the evidence. Yet straightforward doesn't mean ironclad. And experts, seasoned researchers with solid reps and histories, insist we ought to entertain that the figures clash because we might be sizing up an entirely different beast. Part 7. The Mothership Idea, Relic from the Cosmos. Now we venture into murkier, chillier depths. The mothership, the idea, or more broadly, the artificial object theory proposes that 3I/Atlas could entirely be an artificial creation rather than a genuine comet. It might represent a constructed entity, dispatched from afar, perhaps an interstellar spacecraft, inactive, in hibernation, or even functioning, currently traversing our solar system while expertly impersonating a comet. To set the record straight up front, this isn't the prevailing opinion. It's not NASA's stance, nor the consensus among most stargazers, though it's gaining traction mainly through Avi Loeb and a handful of associates, with points that merit genuine consideration, even if you end up dismissing them. After all, scientific advancement thrives on exploring other possibilities, not brushing them aside immediately. At the heart of the artificial object case lie unusual statistical odds and odd behavioral traits. Loeb's stance, outlined in numerous online articles and talks, asserts that basic probability dictates we ought to spot myriad tiny interstellar wanderers long before stumbling upon a massive one. The typical size spread of cosmic junk flung from other star systems should overwhelmingly tilt toward diminutive items, grains, rocks, perhaps minor asteroids, while giants around 5 kilometers across remain exceptional. Encountering such a behemoth as merely our third verified interstellar find strikes Loeb as fishy. It's akin to drawing 3 random sea creatures and pulling up a massive mammal. Conceivable, sure, but it prompts questions about whether we're misunderstanding the overall makeup. Plenty of experts challenge this reasoning, highlighting the massive sway of observational biases. Current setups prioritize the most luminous and conspicuous candidates due to sensitivity constraints. As our instruments advance, we'll pick up tinier, dimmer interstellar objects, and the scale of sizes should even out. That whale isn't scarce. It's simply the lone catch our current tools can snag. Loeb concedes this point yet contends that, even factoring in those biases, the figures are slim enough to demand closer examination. The argument's next foundation involves the faint non-gravitational push amid evident gas release. We've covered the offsetting jets theory, which feels organic and reasonable. Still, Loeb observes that such balanced outflows demand a particular, rather forced setup, several venting spots whose force directions precisely offset each other. Feasible, yes, but it smacks of tailoring the explanation to match the observations. On the flip side, should the entity be expelling material not for heat relief but deliberately, say, for maneuvering or regulating onboard tech, it could produce just this signature. Noticeable haze from the discharge, yet little overall motion thanks to deliberate or balanced control. The final leg concerns the path it takes, and I must proceed cautiously since the observations don't truly back claims of an irregular route for 3I/Atlas. Its path forms a hyperbola, aligning with extraterrestrial routes, and the tilt plus entry direction falls squarely within norms for a chance visitor. It isn't slicing straight across the planetary plane in a manner hinting at purposeful scouting. No signs of slowing or steering. From what we observe, it's following a straight inertial course. That said, Loeb and like-minded thinkers suggest that a covert probe designer would steer clear of blatant adjustments revealing its origins. Instead, it would glide along a route appearing ordinary, rely on unobtrusive monitoring over probing scans, and release vapors, when needed, to ape comet activity. Put differently, the lack of clear tech markers doesn't confirm it's natural. It could reflect savvy design. In its boldest version, this claim resists direct testing, rendering it irksome for rigorous inquiry. Yet it's key to remember that no proof doesn't equate to proof against, a notion that swings both directions here. So what might tip the scales toward the artificial theory? That's the crux. For starters, consistent directional shifts. Should 3I/Atlas alter its course in manners unaccountable by gas effects, it'd be definitive proof. Acceleration sideways from the sun's pull, when it ought to slow, or a targeted pivot impossible for natural causes would seal it. Next, mirror-like gleams, or surface flashes. Organic forms tend to be jagged and uneven. Engineered ones, like solar arrays or reflectors, yield intense, pinpoint bursts of light at certain sun angles. If imaging data revealed abrupt luminosity, surges recurring at intervals tied to spin, it'd point to smooth, shiny panels. Finally, focus signal emissions. Comets yield wide-ranging heat glows and reflected rays. Should radio arrays pick up a narrowband broadcast from 3I/Atlas observing lasers at a precise wavelength, one that doesn't align with any known molecular emission, would serve as compelling proof. Next, non-thermal radiation. Should infrared data reveal the body heating up more than mere sunlight could account for, it could suggest an internal energy source. That said, we'd first have to exclude possibilities like heat from buried radioactive elements or gravitational tidal forces. To date, nothing like this has shown up. The path follows a straightforward gravitational arc. No unexpected flashes or bounces of light beyond those typical of a rough, frozen exterior. Zero radio transmissions. The heat signature, as far as we can gauge it, matches what the sun would produce. Loeb's take boils down to dig deeper. He points out that the reluctance to hunt for technological signs has led researchers to skimp on the targeted scans that could spot them. If nobody's truly scanning for signals or odd path changes, naturally we won't detect any. He pushes for bolder surveillance, finer timed light measurements, broader spectrum scans. And honestly, he's spot on. If we just presume it's ordinary and skip checking for artificial hints, we'll miss them even if they're obvious. It's reminiscent of the Oumuamua saga, which bears another look. Back when Oumuamua displayed that bizarre speed-up with no clear cause, Loeb along with Shmuel Bialy put out a study floating the notion of a solar sail, a lightweight mirror-like film driven by stellar light pressure. The theory went that if Oumuamua was engineered thin, akin to foil, sunlight could nudge it along to fit the scene motion. They phrased it cautiously, listing the sail idea as just one hypothesis among many, not a bold assertion. The backlash hit fast and divided. Certain news sources spun it into Harvard expert claims Oumuamua is ET ship blasts. Fellow scientists fired back, insisting everyday causes like hydrogen venting or nitrogen frost vaporizing made way more sense. Things got tense, even nasty at times. Loeb faced charges of chasing fame. Detractors got called out for being too rigid. Real science got mixed up in press spin and career jostling. The key takeaway from all that chaos? Bold ideas demand solid backing, sure, but that bar can't twist into don't even think about it. If you start with zero chance for alien tech, no proof will ever sway you since you've dismissed it up front. That's not inquiry. That's rigid belief. A better stance. The odds are slim but not nil, and evidence shifts them. Loeb's approach aims to map out that evidence shift. Right now, facts like JWST spotting common icy compounds and no signs of deliberate steering heavily favor the comet theory against the made-by T1. The light patterns match frozen water exactly. The dust clouds form and changes scream comet. Every checkable trait acts cometary. So Occam's rule leans comet. Yet Loeb counters that Occam's rule is advice, not ironclad, and the easiest answer can flop. Now, on the clash between press hype and careful science. Big players like NASA, ESA, and academic teams shy from threat scare angles. For good reason, no proof of malice. No proof of purpose. Labeling it a danger when it's clearly not aimed at us and acts passively is just stoking panic. But there's also a baked-in wariness in the system. Public space outfits rely on taxpayer cash. Their experts guard their standing. Backing a wild guess that flops can tank a livelihood. So the setup favors playing safe, which often works, but it can also stifle valid probes into outliers. Hiding a vessel by mimicking a comet isn't impossible theoretically. You'd release stuff with light fingerprints like regular space ices. H2O, carbon dioxide, carbon monoxide, basic carbons, all producible or carried. You'd time releases to dodge thrust that flags as control. You'd form the thing to dodge radar pings and skip sharp edges in visuals. You'd glow heat-wise as if just sunbaked. Advanced enough tech could pull it off. The real puzzle, would anyone bother? That loops to the Stealth Scout idea, a classic in SETI musing. Picture a superior society sprinkling the stars with self-running devices that lurk, watch, or gather info, staying quiet till a signal wakes them. These gadgets wouldn't broadcast, they avoid pointless movements. Instead, they simply glide along, observe quietly, and bide their time. For a wary society fretting over the dark forest idea, where showing yourself could lead to total destruction, sending out stealthy scouts fits perfectly as a tactic. You gather intel without risking detection. Yet, the issue here is that this theory bends to fit anything. If you're ready to assume ultra-advanced cloaking tech, every anomaly could pass as such a scout. That renders it impossible to disprove. And ideas that can't be tested scientifically? They're worthless for real progress. You require predictions you can actually check. Lowe's work aims to spell those out clearly. Scan for deliberate shifts in path. Hunt for glints off surfaces. Probe for unnatural signals. Run those checks and come up empty? The idea loses steam. Spot something odd. It gains traction. There's a governance side to this as well. Suppose there's just a 1 in 10 shot that 3i/Atlas is something built by others. How would space agencies adjust their approach? Would they fast-track high-res photos? Try sending messages? Kick off routines for surveillance and pursuit? Right now, cosmic regulations lack a solid playbook for dealing with possible extraterrestrial gadgets. The Outer Space Treaty covers land grabs and armaments up there, but it's vague on managing suspect probes from afar. SETI guidelines cover reacting to radio pings, sure, but those are optional and unproven in practice. Let's not ignore the pushback within the field. Jason Wright, an astronomer at Penn State and astrobiology expert, has openly challenged parts of Lowe's arguments on dimensions and data analysis. He contends that Lowe's reading too much into fuzzy readings, and that the scaling by frequency falls apart when you factor in all biases and unknowns properly. No bad blood here. This is just experts holding each other accountable, double-checking calculations, probing premises, tweaking frameworks. Disagreement like this is a good sign. It shows the topic's getting the rigorous debate it deserves. So, how does the idea of a command vessel hold up post the recent Mars flyby? No path adjustment spotted? Coma acting like typical gas venting? Perihelion passes without drama? Then the odds of it being built drop more. The anomaly score would keep sliding down. Still, without snapping direct pics of the core or picking up clear signs of tech, we can't dismiss it completely. That lingering doubt is what sustains the notion, lingering like a shadow in the readings. Now, shifting to the third possibility, the one that's oddly more believable than a flagship, yet more disturbing overall. Section 8. Smarts or just chance? The Dark Forest discussion. Silence demands our attention. If 3i/Atlas, or Oumuamua earlier, or whatever interstellar wanderer shows up next, proves engineered, one burning question hits. Why no greetings? Your take hinges on your preferred view of interstellar mindset. The Dark Forest concept, made famous by Liu Cixin's sci-fi series but drawn from classic game theory, runs like this. The cosmos teems with smart societies, yet they're all in stealth mode. Reason? Broadcasting your spot is asking for trouble. Any group savvy enough to catch your broadcast might also be equipped to wipe you out over resource scraps. Thus, the smartest play, the sole path to lasting, is quiet. You eavesdrop, but stay off air. You watch, but stay hidden. The woods stay shadowy not from vacancy, but from all the folks crouched behind trunks, barely breathing. It's a bleak outlook, and truth be told, few experts buy it as a straight-up model for star system dynamics. Still, it's a sharp mental exercise for grasping why no clear signals or blatant relics don't prove solitude. Quiet can go either way, empty void, or packed but hushed company. Under the Dark Forest model, if 3i/Atlas is made, it wouldn't beam out. It wouldn't veer noticeably. It'd pose as ordinary rock, merge with the crowd, snag info on the sly, then slip away. Viewed that way, missing tech markers doesn't undercut the built-object theory. It's precisely the pattern to anticipate. Trouble is, this thinking shields the idea from refutation. Spot fake signals. Boom, proof of vessel. No signals. Still fits a vessel. So, what finding could ever sink it? You've built an ironclad loop. The theory weathers every result. And though that feels comforting if you're hoping for cosmic company, it's devoid of scientific rigor. True science demands the possibility of falsification. You have to be able to declare that spotting X would disprove the idea. Lowe's method navigates this challenge by turning the idea into a matter of probability instead of a simple yes or no. Rather than wondering if it's extraterrestrial, he's evaluating the odds of it being alien based on the evidence at hand. That likelihood, rated on his scale from 0 to 10, can rise or fall as new information emerges. At the start, with sparse details and a few oddities, you could give it a middling score. When additional findings reveal ordinary patterns, the rating declines. Should clear signs of technology emerge, it jumps to the maximum. Close-up photos revealing a typical comet core would send it crashing to nothing. This setup permits revisions, which aligns with proper scientific practice. Experts generally agree that the starting odds for any specific interstellar visitor being man-made are tiny, perhaps 1 in a million or even a billion. Overcoming that baseline requires overwhelming proof. You demand several separate pieces of supporting data, each suggesting advanced tech. A single quirk won't cut it. A pair might just be chance. A trio begins to suggest a trend, yet you'd first exhaust every natural cause. This leads into the social side of things. The internet detectives, the leaked snapshots, the pareidolia. In our era of social platforms and rapid news, every fuzzy photo gets pored over by hordes of hobbyist examiners. One person notices a slightly glowing dot next to its peers and proclaims it a solar panel gleam. Another detects a light shift and labels it a directional tweak. Our minds are built to spot designs, even amid randomness. We perceive faces in the sky, creatures in Rorschach tests, and plots in random events. This isn't deliberate deceit, it's just how cognition works. Yet it fosters an online environment where bold assertions propagate quicker than measured counterarguments. A story headline blaring "Alien device spotted" racks up millions of views. The subsequent clarification, "Nope, merely a comet with quirky composition," barely hits thousands. The debunking lags behind the hype, and this imbalance taints discussions, complicating efforts by researchers to convey subtleties. Longtime SETI researchers, who've spent lifetimes hunting for signs of cosmic minds, usually balance hope for discovering otherworldly beings with profound doubt toward specific reports. They've witnessed countless red herrings. Pulsars once seemed like ET signals, inspiring the playful acronym LGM for Little Green Men, before we identified them as spinning neutron stars. The WOW signal, a potent narrow radio burst caught in 1977, remains puzzling and unrepeated. Fast radio bursts baffled us until natural cosmic origins surfaced. The cycle repeats: early buzz, guesses of intelligent sources, ultimate mundane resolution. Thus, the SETI crowd's view on Oumuamua is straightforward: bring the evidence. For any maneuvers, we require the positional measurements. For radio emissions, verification from various observatories. For shiny surfaces, detailed visuals. Absent that, it's a comet. Still, consider the hypothetical. If crafting a covert pass through an unfamiliar star system, how would you proceed? You'd enter from beyond the ecliptic plane, where planets mostly circle. This avoids the busiest clutter zone and reduces chances of early spotting by monitors targeting ecliptic-adjacent items. Next, you'd suppress detectable outputs. Skip thrusters if possible. Avoid broadcasting. If dissipating warmth, imitate ordinary heat glows. Finally, you'd schedule your path to extend viewing windows while steering clear of hazards. Now, does Oumuamua's real path fit this blueprint? Hardly. Its tilt above the ecliptic is higher than average, but that's standard for wanderers unbound to our system's spin. The route lacks hints of strategic scouting angles. It doesn't weave through the core zones to brush by numerous worlds. It's simply barreling across, direct entry and exit. If this was an engineered reconnaissance, it's remarkably sloppy. An optimal one would tweak the course for several key stops, perhaps leveraging gravitational slingshots. Oumuamua engages in zilch of that. It acts like a passive hunk of rock, precisely as a cosmic drifter should. But advocates of the dark forest theory might argue back. Perhaps optimization isn't the point. The aim could be blending in. A path that's overly shrewd, hitting too many prime spots, would raise flags on its own. It's smarter to glide by on a dull route, gather whatever observations are possible, and move on. The probe idea trades off data precision for safety in operations. Once more, we're circling back to the issue of unfalsifiability. Any bit of proof can get twisted to back up the idea if you're inventive enough. That isn't real science. It's just crafting a tale. Now, consider the impact of echo chambers and how algorithms amplify things. Social networks chase engagement, so they promote stuff that sparks intense responses. Wild assertions, like aliens arriving or a government hiding the truth, stir up big reactions. Meticulous scientific breakdowns? Not so much. As a result, algorithms flood millions with those flashy claims, while counterarguments fade into the background. This builds info silos where folks mostly see material that reinforces what they already think. Craving to see 3i Atlas as a mothership? Your timeline will bombard you with supporting posts and skim over the critics. This challenge isn't fresh, but it's exploded in severity over the past 10 years, turning science outreach into a real battle. How do you go up against a trending post claiming a Harvard expert verifies alien ships, when the truth is that expert floated a theory dismissed by peers? You don't stand a chance. The subtleties vanish, doubts disappear, and everyone ends up with a skewed view of scientific knowledge. Outlets like AP News, NASA statements, and ES announcements all hammer home the identical point. No danger, behavior matching a comet, origins probably natural. These are the trusted voices, yet they're dry and official. They fail to ignite the feelings that drive shares and discussions, so their audience stays small next to hype-driven material. What could disprove the artificial craft theory? That's the key query. Should 3i Atlas zip through perihelion and stick to a straight ballistic path without any adjustments? It deals a major blow. Ongoing chemical scans revealing just everyday comet gases, devoid of factory-made substances or weird isotopes. Another hit. Eventually, sharp images exposing a standard comet core, lumpy and stony, would bury the notion for good. Spotting several more interstellar visitors in the future, all acting cometary with sizes that fit statistical patterns, would dismantle the rare giant excuse. On the flip side, what might validate it? One obvious adjustment impossible to chalk up to gas vents. A radio burst, even fleeting, on a bizarre wavelength. A mirror-like bounce off a smooth panel. Shapes hinting at design in photos. Any such find would shift everything, but only if it's repeatable, backed by various tools, and defies easy natural accounts. A fuzzy snapshot won't cut it. A dubious reading won't suffice. You require ironclad, crystal-clear proof. The mental angle here matters a lot. Humans hunt for patterns instinctively. Our forebears stayed alive by spotting threats in the gloom and decoding motives from faint signals. That brain wiring doesn't switch off amidst our data. A glitchy spot turns into a window. A wiggle becomes a dodge. An unusual element mix screams evidence. We fill in the blanks since gaps unsettle us. We'd rather embrace false assurance than embrace true doubt. Recognizing this tendency is the starting point for rigorous reasoning. When you're tempted to leap to a judgment, stop. Consider what facts would have to hold for that judgment to fail. Hunt for other interpretations. Insist on superior evidence. Science means mastering the skill of avoiding self-deception, and you're your own prime target. So, as 3i Atlas swings by Mars this evening, where does the dark forest discussion land us? If it's a stealthy scout, detection might only happen through blatant artificial moves. If it's an ordinary comet playing it low-key, we must resist inflating the readings. The quiet, the absence of tech traces, reveals zilch since it fits either case. We're after affirmative clues, something decisively tilting the scales one way or the other. To date, those clues lean comet. Yet there's another possibility we haven't dug into completely, a weird hybrid zone between organic and engineered. Suppose 3i Atlas isn't a working entity, but a fragment of one? What if this is wreckage from an ancient, remote disaster? Part N. The wreckage swarm idea. Fragments from a far-off apocalypse. Picture a planet perishing not gradually across eons, but in sudden, brutal fashion, spanning mere hours or days. Perhaps it strayed too near its home star, where tidal pulls tore it to bits, scattering it into a cascade of shattered pieces expanding into the void. Or consider two worlds smashing together in a stellar pileup at speeds of tens of kilometers per second, obliterating the intruder and fracturing the victim into chunks. Alternatively, a wandering star might have barreled through the system, its gravity yanking planets off course and hurling them into wild paths. Each of these possibilities could generate precisely the kind of sight we have here. Hefty, oddly formed remnants loaded with specific gases tumbling across the galaxy along straight-line routes. That's the core of the debris field theory, and it holds up remarkably well. Our own solar neighborhood offers real-world examples of such planetary mayhem. The asteroid belt could represent the leftovers of a world that failed to coalesce, or one ripped apart by Jupiter's massive pull. Saturn's delicate rings likely stem from a satellite that ventured too near and got ripped to shreds by gravitational tides. We've even witnessed tidal shredding around black holes and distant suns, tearing apart bodies in far-off setups. The underlying physics is solid and predictable. Far murkier, though, is how those resulting bits might hold onto gases like water and CO2 for eons while adrift in the void, and if they'd resemble the features we're spotting in 3I Atlas. Let's break down the process. Tidal breakup occurs when the pull differences across an object overpower its self-gravity. That's the Roche limit in action. For a stone-like form hugging a star, it's usually just a handful of star radii away. Venture inside, and the thing gets stretched and torn. The event is brutal. Elongation, splitting, scattering. Debris blasts out fast, some plunging into the star, the rest fleeing outward. Now, suppose the torn-apart body was a frozen giant, like an oversized comet or a mini-planet packed with volatiles. Its pieces would haul those materials along. The snag? The outer shell heats up and partly evaporates in the chaos, leaving behind oddball fragments, maybe tougher stuff on the outside, with softer ices locked within. Ring any bells? It mirrors the setup we've outlined for 3I Atlas, a weathered outer layer trapping gases in an off-kilter mix. Experts have delved into tidal shard origins for objects like Oumuamua. Several papers suggest its stretched form and quirky speed-up could arise from being a sliver of a ripped nitrogen ice world, akin to Pluto. The theory paints it as pancake-flat and shiny, nudged by sunlight like a makeshift solar sail, yet purely natural. Not everyone buys it, but it shows the shard idea has gotten real scrutiny for past cosmic drifters. For 3I Atlas, picture this scenario. A massive frozen mass, say 1,000 kilometers wide, gets mangled by a star or gas giant. The result? A spray of wreckage, from fine grit to boulder-sized bits. These get flung at blistering speeds, tens of km/s, in all sorts of angles. Across millions of years, they fan out, yet stick to parallel paths due to their shared starting point. A few wander into the interstellar expanse. In this view, 3I Atlas is one of them, a big one, spanning several kilometers from the heart of the original. Its CO2 abundance comes from the event stripping watery surfaces first, exposing hardier inner frosts. The outer shell bears scars from long exposure to radiation, tweaking the makeup further. As it swings into our system and heats, the shell fractures, releasing sealed gases. We spot a hazy tail like a comet's, but the makeup's lopsided from its rough past. If true, what signatures would show in the light analysis? Expect gas signatures. We're already picking up CO2, water vapor, carbon monoxide, and perhaps sulfur compounds like carbonyl sulfide. You could also find weird dust particles, holdovers from the smash-up that never reformed. The dust-gas balance might diverge from standard comets. Early JWST data teases some of these traits, but it's not locked in yet. The real puzzle, where's the rest of the group? A debris trail implies siblings on matching routes. They won't cluster tight. Tidal events scatter stuff across vast spaces. Still, wide searches ought to spot others with alike speeds and makeup. None have turned up so far, no trailing pack in the logs. But absence isn't disproof. It could just mean the others are too faint it's tough to spot them all, or perhaps they're following paths that won't cross our observational range for years or even decades to come. Or maybe 3I Atlas truly stands alone. There's a demographic angle to consider as well. Should tidal debris flows represent a major origin for interstellar visitors, we'd anticipate groupings in their velocity patterns. Items stemming from one breakup incident ought to share comparable velocity and heading at first. Across millions of years, those paths spread out thanks to pulls from nearby stars and the galaxy's tidal forces. Yet for fresher flows, perhaps just a few million years in age, such groupings should remain visible. With more interstellar object sightings piling up, we can begin searching for those patterns. Spotting them would bolster the case for scattered wreckage theories. If each object appears utterly standalone, the idea loses steam. Now, consider the deeper implications on a philosophical level. If 3I Atlas is a remnant from a shattered planet, we're essentially examining the aftermath of an extraterrestrial disaster through its geology. We're witnessing the final echoes of a world or satellite that perished eons ago in a stellar setup we'll likely never pinpoint. There's a deep sense of sorrow in that image. It's like a gravestone wandering the emptiness, a fragment from a lost realm, devoid of any biology or data, bearing only the traces of its explosive demise. Yet it's riveting from a research standpoint too. By studying these pieces, we gain insights into the cores of planets orbiting distant suns, obtaining actual specimens shaped by unique environments and compositions, maybe near stars of varying metal content or lifespans. It's like planet science compared across the stars. Each wandering chunk serves as a gratis specimen from the universe's inventory, and we don't need to launch probes. It delivers itself right to our doorstep. Getting the message across about risks matters a lot. Even supposing 3I Atlas is a kilometer-sized sliver from a wrecked body, it poses zero threat to our planet. Its nearest pass remains roughly 270 million kilometers away. Should it break apart more near its closest solar approach, which seems improbable considering its chill temperature and the mild warmth from the sun at 1. For Australian dollars, any subpieces would stick to the identical outgoing path. They wouldn't veer abruptly toward us. The rules of orbital paths don't allow it. Shifting a hyperbolic course to one that intersects Earth demands a huge velocity shift, something needing either propulsion tech or a planetary slingshot. Nothing like that's in play. But selection effects come into the picture too. Big chunks are uncommon, though feasible. In a breakup that yields a power law spread of sizes, you'd get loads of tiny bits alongside some giants. The giants are simpler to pick up on, so we spot them before anything else. As detection tech advances, smaller ones should enter the tally, rounding out the size profile. Discovering a big one so soon doesn't prove giants abound. It could simply indicate we're still grabbing the obvious targets. Modeling offers another angle. If these bits arrive in flows, their tilts and timing might reveal faint links. You wouldn't see exact matches, since the initial scatter imparts diverse speeds, and ages of wandering fan them further. Still, if you crunch the paths of various interstellar objects and notice some bunching in key traits, that hints at shared routes. We lack the dataset for such checks right now. 3 examples don't make a robust set. But at 30 or 300, trends could surface. And should this framework hold, it reshapes how we view the space between stars. It's no mere vacuum dotted with specks of dust and gas atoms. Instead, it's laced with rubble from shattered solar setups, the husks of failed worlds meandering endlessly until they brush another system. The Milky Way turns into a vast cemetery, and we're only beginning to decipher its inscriptions. Yet there's a grimmer twist lurking beneath this discussion. Suppose 3I Atlas isn't a lone survivor? What if it heralds a sequence? Chapter 10, The Apocalypse Flow. Let's dive into wild speculation for a bit. Picture a stellar realm, perhaps hundreds or thousands of light years off, hit by a calamity too immense to grasp fully. A colossal stellar outburst, a billion-fold fiercer than our sun's worst, wiping out inner worlds and scrambling the outer belts. Or a smash-up of massive gas giants, unleashing power like millions of atom bombs and spawning wreckage spanning billions of kilometers. Or a wandering star barreling through at breakneck pace. Whatever the cause, the outcome is a trail of wreckage, bits from fine particles to chunks spanning tens of kilometers wide, all hurled out on comparable paths, hurtling across the void at speeds of dozens of kilometers per second. Eons go by, perhaps millions or even billions of years. The pieces fan out, yet they remain somewhat grouped together. A flotilla of ruin gliding silently in the blackness. And purely by luck, this trail is now crossing paths with our solar system. Oumuamua was the initial one spotted. Borisov came next. Then 3I/Atlas marks the third. Should the debris trail idea prove true, others are on the way. Could be tens, maybe hundreds, varying in size from tiny to massive. We'll catch some early with our instruments. Others might slip by undetected until they've zipped past. The vast majority will sail harmlessly far from Earth. Yet over repeated close calls, odds suggest one could come perilously near. This outlines the apocalyptic trail concept, and I must stress, it's purely hypothetical and proven conjecture. No formal warning ties these three bodies to one debris flow. Nothing indicates additional ones inbound. This represents the grim, nightmare-fueling extreme of the wreckage cloud theory. Still, it's circulating in discussions, especially among web forums fueled by cosmic anxiety. So let's tackle it head-on with straightforward facts. The initial query: does the sequence even stand? We've confirmed 3 interstellar visitors in just 8 years. Oumuamua in 2017, Borisov in 2019, 3I/Atlas in 2025. That works out to roughly 1 every 2 or 3 years. A genuine uptick, or merely sharper eyes spotting them? Truthfully, it's likely the latter, better tech at work. In the past 10 years, skyscanning gear has leaped forward. Scopes pick up fainter signals. Analysis crunches data quicker. AI-driven spotters are sharper than ever. We're scanning broader swaths of the heavens, more frequently, with superior equipment, uncovering more cosmic travelers. That's no surprise. Spotting 3 interstellar objects over 8 years doesn't prove a surge in visitors. It could simply reflect our newfound skill at detecting the steady drizzle that's always fallen through. That said, suppose the trail theory holds water. If these 3 hail from a shared catastrophe, what signs would we anticipate? For starters, matching speed and direction. They'd travel in a similar heading at comparable paces, adjusted for gravitational tugs from our sun during each pass. Next, alike makeup. Their spectra should reveal traces pointing to birth in the identical stellar neighborhood. Finally, timed arrivals. In a trail, they wouldn't pop up haphazardly. Arrivals would bunch up, mirroring the trail's varying thickness. Do these 3 fit the bill? Time to examine. Oumuamua's hyperbolic speed topped out around 26 kilometers per second. Borisov clocked in at about 32 kilometers per second. 3I/Atlas barrels at nearly 58 kilometers per second inside the inner system, but its unbound velocity, post-sun adjustment, drops lower. Not exact matches, but in the same league. That's a mild knock against the trail idea. Interstellar drifters can vary in pace based on how they formed and got flung out. On makeup, Oumuamua lacked a dusty tail, leaving us data scarce. Theories range from frozen nitrogen to hydrogen ice or a fluffy dust ball. Borisov resembled typical comets, loaded with water and akin to our own system's icy wanderers. 3I/Atlas, however, brims with CO2, diverging from the others, no obvious link. That's a firmer blow. A common shatter event should yield closer resemblances. As for timing, Oumuamua arrived October 2017, Borisov August 2019, with perihelion in December. 3I/Atlas found in July 2025, nearest to Mars today, October 3rd, gaps of about 2 years, then 6. No steady rhythm. For a trail, it'd have to be exceptionally stretched or thin out. In the end, data-wise, linking these 3 to one debris trail looks shaky. They seem like solo travelers from varied stars, aligning with mainstream expert views. Crucially, though, our dataset remains minuscule. 3 examples scarcely set a standard, much less reveal trends. More finds are essential. Enter the Vera C. Rubin Observatory. Rubin, once called LSSD, the Large Synoptic Survey Telescope, is gearing up for launch imminently. It'll sweep the full night sky every few evenings, catching dimmer targets than today's setups manage. Projections say Rubin could nab interstellar objects yearly, or even faster. In 10 years, we might tally dozens of verified ones. Only then can solid stats take shape. That's when any trails, if real, would show themselves. If the trail is out there, here's what we'd seek out. A series of interstellar objects, ISOs, spotted in the coming years, all sharing comparable speed directions and chemical signatures. Hits from tiny meteoroids on satellites revealing odd density levels or makeup that aligns with the flow's forecasted path. Peculiar shifts in the infrared backdrop, minor fluctuations in the faint IR shimmer across the heavens hinting at an unexpected buildup of particles. So far, nothing like this has surfaced. Efforts to hunt for these clues continue, though they're tough since the cosmos buzzes with interference and the traces would be faint. Now, consider how better telescopes shift the odds. The Rubin Observatory will pick up items as dim as magnitude 24 or 25, astonishingly subtle. To put it in perspective, the dimmest stars you can spot without aid top out at around magnitude 6. Every magnitude jump means 5 times less light. Thus, magnitude 25 appears roughly 400 million times dimmer than what the eye can catch. With that level of sharpness, Rubin should uncover modest asteroids, far-off comets, and indeed, interstellar visitors that earlier scans overlooked completely. This goes beyond boosting discovery numbers. It reshapes the profile of what we find. Right now, our view favors bigger or more vibrant bodies since they shine brighter. Rubin will reveal tinier, dimmer ones, rounding out the smaller sizes in the lineup. Should we begin spotting scores of little ISOs for each big one, that fits with what we'd expect from natural flung-out groups. If the balance keeps tilting to giants, though, that'd be oddly off and could bolster Lowe's data-driven claims. Shifting to the idea of building tension. If this flow is real, might subsequent pieces be bigger or nearer? Theoretically, sure. Wreckage flows aren't even-keeled. They feature uneven spots, clusters, and voids based on how the original breakup unfolded. If we're brushing the front of such a flow today, the core mass might swing by in years or even decades. Yet bigger or nearer doesn't spell peril on its own. A 10 kilometers chunk zipping past at the same range as 3I Atlas, around 270 million kilometers from our world, poses zero risk. It would take a collision course and path that crosses Earth's route precisely. For something on a hyperbolic path from beyond our system, that's incredibly rare. The setup simply doesn't line up for it. Experts in planetary protection, whose job is fretting over rock strikes day in and day out, zero in on sun-tied near-Earth objects. Those are the dangers we can monitor, forecast, and maybe nudge aside. Interstellar arrivals form another class. Their timing feels utterly haphazard. We could get weeks or months heads up, based on their glow and when detectors nab them. But steering one at 50 to 60 kilometers per second? That's beyond our tech, which struggles with sluggish, charted rocks already. An ISO barreling through the sun's inner turf at cosmic speeds. We'd just observe its flyby and cross our fingers. To stress the point, AP News, NASA, and ESA all stress that 3.2 Atlas carries no danger. Its nearest pass to us exceeds 250 million kilometers. Even with breakup or hidden sidekicks, the paths of motion won't permit an abrupt turn toward Earth. Armageddon would demand not merely a debris trail, but one aimed dead-on at our home. The odds of that? Next to nothing. The void is immense. Our planet is minuscule. A fluke strike would take cosmic-scale misfortune. So what's the status of this flow idea? It's something we can probe, and that's a plus. In the years ahead, spotting several ISOs with linked traits would strengthen it. If each one seems standalone, the notion weakens. It's a bold guess, but science welcomes those if you flag them right. And it doesn't signal any urgent peril, even if it would alter our view of the space between stars and perhaps call for tweaks in defense plans down the line. The deeper insight here runs deep. A real flow would show the galaxies far more restless than we thought. Disasters in remote stellar setups send ripples spanning light years and ages. The cosmos isn't a bunch of standalone zones. It's linked, brutal, and marked by old wounds. A debris current slicing our system's space would underscore that we're woven into that grander, wilder expanse. No cozy shield around us. We're sailing amid the ruins of failed planets. But checkable forecasts turn this into solid inquiry, not just musing. Keep an eye on fresh interstellar finds soon. If another boasts CO2 abundance like 3 Atlas, take note. If its speed path echoes the pattern, lean in. If trends emerge, the flow theory jumps from guesswork to that makes sense, at least in theory. For now, though, it's just a potential scenario, not something likely to happen. This leads us right into the issue of information delays, the space between spotting something and sharing it publicly, and why that fuels suspicions of cover-ups. Episode 11, The Secret Battle Over Data. Let's dive into the timeline from when a telescope first grabs an image to when it hits the news feeds. That interval, full of delays that can spark real frustration and worry, is prime territory for wild theories to take root. Here's how the standard process unfolds. Picture an observatory like Hubble, the James Webb Space Telescope, or one of ESA's Mars probes locking onto an object. The incoming info arrives as unprocessed light signals turned into digital files. This initial data is riddled with glitches, stray hits from cosmic rays creating bright spots, background static from the instruments, shifts in calibration, and built-in biases from the setup. To turn it into something reliable for research, it has to go through cleanup. That involves layering on calibration adjustments, removing stray light, fixing distortions from the atmosphere or hardware, and transforming the readings into real-world measures like intensity or wavelength output. This cleanup isn't quick. It might take hours for basic photos, days for detailed light analysis, or even weeks if the data is quirky or needs tailored tools. After processing, the research group digs in. They run simulations to match patterns, cross-check against expected models, ensure it lines up with prior findings, and draft reports, often as academic papers or internal notes. Next up is the review stage, where experts scrutinize the work, poke at the techniques, and recommend tweaks. That phase can drag on for weeks or months. Only then, if everything checks out, does the full report land in a journal or go online as a draft on AR-14. Running parallel is the outreach side. If the discovery's buzzworthy, the organization might drop a news bulletin. Reporters in the science world pick it up, craft stories, and those pieces ripple out via social platforms until everyday folks catch wind. From initial capture to breaking news, the timeline might span weeks to months or more. That's standard operating procedure. Science demands precision, thoroughness, and patience. From an outsider's view, though, especially if you're buzzing with curiosity or nerves about potential breakthroughs, it can come off as shady. They spotted this thing ages ago. Why no updates? What's getting buried? Most often, 99.9% of cases, the truth is straightforward. They're grinding through the rigorous steps of real science, which isn't flashy or fast-paced like social media scrolls. Still, here's a key point. The clash between official announcements and quick online buzz does widen that trust divide. Take Oumuamua as an example. Hobby stargazers and data buffs were poring over open tracking logs and guessing at the visitor's traits well before any formal statements dropped. Once those did emerge, they occasionally dialed back or refuted the more dramatic takes. To skeptics, it screamed suppression. They're dialing down the hype because they've got insider knowledge. In truth, it's simply the gap between rough guesses and polished verdicts. First-pass ideas frequently miss the mark. Readings get refined. Forecasts evolve. Established sources hold off until they're solid, which is smart but sluggish. Meanwhile, the web crowd races ahead, prioritizing pace over precision. Each approach has merits, but they run on mismatched clocks and motivations. With C/2023 A3, Sachin Shenatlis, folks at NASA's Goddard Center released a quick overview piece on JWST's findings. It spotlighted the odd carbon dioxide-heavy haze and lopsided form. That's openness in action. They're laying out the basics. But it's condensed, not the complete package. The detailed light profiles and adjusted readings? Those are gearing up for a formal publication. Once it's out, peers can grab the files, test their own interpretations, and verify the results. That's the beauty of the setup. ESA chimed in too, noting that Mars Express and the ExoMars Trace Gas Orbiter would scan C/2023 A3, Sachin Shenatlis, from October 1st to 7th. They've shared progress snippets on their sites and feeds, but the polished visuals and breakdowns will follow once the raw stuff's vetted and crunched. Standard stuff, sure, but the weight stokes unease all the same. Finally, consider how the press ramps things up. Flashy stories, whether hyping extraterrestrials or slamming them hard, travel way quicker than even-handed breakdowns. A screamer like "Massive ET craft nears the red planet" racks up 1 million shares. Something measured, like "Interstellar visitor reveals bizarre makeup," experts probe further, might hit 10,000. It's wired into our brains. We chase the fresh and the scary. A thoughtful, even-keeled report doesn't pack the same punch, breeding a space where the noisiest takes rule. That pulls in media that dive headfirst into the folks chase the extraterrestrial narrative because it pulls in viewers. Meanwhile, you have media outlets that dive headfirst into debunking, since going against the grain also boosts clicks. The true scientific center, where we admit we're still figuring things out and outline the steps to uncover more, gets pushed aside. It's too tame for the sensationalists and not conclusive enough for the skeptics. So why do assurances like "no danger here" echo so frequently? Well, during infrequent incidents, it's the duty of organizations such as NASA and ESA to calm the public. When odd events unfold, anxiety spreads. Folks start picturing doomsday possibilities. It's up to those agencies to state plainly and often, this poses zero risk. Sure, it might seem repetitive to dedicated followers, but newcomers tuning in for the first time crave that comfort. Shifting gears to media savvy. This is where you can steer the conversation yourself. Spotting a statement about 3I Atlas? Probe its origins. Does it stem from a peer-reviewed study? That's the pinnacle of reliability. A preprint on AR-14? Solid ground, as it shows researchers are ready to stake their reputation and invite critique. A bulletin from a trusted body? Respectable, but keep in mind those can gloss over details or amp up the excitement. Now, a personal blog, social media post, or online clip. Approach with caution. Plenty aren't inaccurate, yet they're rawer, more susceptible to guesses and slip-ups. Tracking references is key. This talk draws from a wealth of them: NASA sites, ESA announcements, AR-14 uploads, Associated Press reports. That's the backbone of credible info. If a person floats an idea without citing roots, or refuses to raise an eyebrow, they might be spot on, but without backup, it's hard to confirm. Treat such assertions with skepticism. Debate in the scientific arena? Far from a flaw, it's the engine. Experts clash over premises and techniques. That pushback spots mistakes and sharpens concepts. Witnessing the clash isn't a sign of disorder. It's proof the system functions. Uniform consensus from the jump? That's the real alarm bell, hinting no one's double-checked the figures. The info skirmish boils down to clashing rhythms. Online platforms demand instant resolutions. Astronomers and labs operate on schedules spanning days to months. That disconnect breeds impatience, which fuels wild theories. Rushing research to match? No, that yields sloppy work. Better to embrace ambiguity as inherent and value waiting as worthwhile. Still, if you're eager to track developments live, try this. Save the Minor Planet Center's entry on 3I Atlas. Fresh positional data lands there as telescopes report in. Scan AR-14 periodically for drafts mentioning 3I, Atlas, or interstellar objects. Tail NASA, ESA, and key observatories on platforms, but skip the flashy titles. Above all, recall that silence from official channels doesn't signal a hidden agenda. Often, it's just a lull before updates. And into that void, conspiracy theories inevitably flood. Part 12, The Tangle of Theories. Okay, strap in. Time to run through some of the more outlandish notions buzzing around 3I Atlas. Let me emphasize, these are guesses, unchecked, and largely proven bogus. Yet they persist. Believers cling to them, and pretending they don't exist won't erase the noise. So, let's expose them to scrutiny and watch what retreats. Start with the clandestine Mars mission footage. The theory posits that a Martian satellite, typically the Mars Reconnaissance Orbiter or Mars Express, snagged sharp photos or clips of 3I Atlas at its nearest pass, revealing clear signs, structured shapes, solar-like panels, perhaps etchings suggesting design. Per the tale, these visuals are real but locked away, lest they spark mass hysteria or expose decades of government awareness about alien guests. Let's unpack it. For one, nothing like that has surfaced publicly or via leaks. Next, should such proof exist and pack a real punch, concealing it would be a Herculean task. Space outfits involve hordes of staff. Researchers exchange notes globally. Findings flow through cross-border teams. Conceiving a blockbuster shot of an ET vessel snapped, then buried, with zero leaks or insiders spilling. It stretches belief to the limit. Plus, the setup of this flyby complicates crisp captures. 3I Atlas zips millions of kilometers from Mars at peak proximity. Even the Reconnaissance Orbiter's stellar lens, ace at mapping Mars from above, would falter at picking out subtle traits on a tiny, remote, speedy target veiled in its dusty envelope. Thus, the notion of such footage being real already crumbles. Some aspects of this remain pretty dubious. But suppose, for argument's sake, that the Mars Reconnaissance Orbiter snapped a photo of 3I/Atlas, and the shot revealed something odd, like a flash that could stem from a smooth plane reflecting light, or a luminosity shift that clashes with expected tumbling patterns. What would follow? The research group would scrutinize it thoroughly. They'd hunt for glitches in the equipment. They'd simulate everyday causes. Should they fail to account for it, they'd release the findings anyway, since puzzling results hold real scientific worth. The notion that they'd bury it forever clashes with the true nature of research. Reputations rise on breakthroughs, not secrecy. Next up, the plot about defense forces gearing up for a rendezvous. The assertion is that the U.S. military or parallel outfits abroad intend to snag 3I/Atlas using a probe, whether to probe it closely or neutralize it as a potential hazard. Twists on this theory posit that secret defense radars have picked up bizarre motions from the thing, swift darts, odd speed-up profiles, and that countermeasures are in the works. Let's ground that in facts. No government body has revealed plans for such a pursuit. Our planet's nearest pass to 3I/Atlas sits at roughly 270 million kilometers this December. Dispatching a vessel to bridge that gap and sync speeds with something zipping along above 50 kilometers per second would demand ridiculous propellant loads and span years en route. That's not feasible in the time frame at hand. Plus, 3I/Atlas isn't dangerous at all. It won't slam into us. There's zero tactical or protective motive to chase it down. The sole rationale for dispatching a craft would stem from pure inquiry, and such ventures demand years of preparation and clearance. We're not firing off probes on short notice. As for those zippy blips spotted by military gear, the Pentagon runs orbital monitoring systems that follow items in space and farther out. Parts of that intel stay under wraps due to the tech's delicacy, but the chance they've caught something about 3I/Atlas that backyard stargazers missed is slim. The comet's path has been mapped by scores of global telescopes. Its spot and pace are pinned down with pinpoint accuracy. Any evasive jinx would register in amateur sky measurements. You can't conceal the rules of space travel from equations. Another batch of theories swirls around purported smuggled clips, fuzzy snapshots, or video bits that supposedly reveal 3I/Atlas up close. Folks swear they spot structured forms, tidy contours alien to nature. Some highlight glow fluctuations resembling navigation beacons or power flares. These visuals spread across chat boards, Discord groups, and UFO/conspiracy-focused subreddits. The issue? Hazy visuals trick the eye. Your mind patches the blanks. You spot patterns you anticipate or desire. That's pareidolia at work, the habit of spotting significance in vague or chaotic inputs. It explains cloud animals, toast savior images, and starships amid digital fuzz. Absent solid provenance, setup details, and origin checks, such pics mean zilch as proof. They might tag wrong solar neighbors. They could flag gear malfunctions. They could be total hoaxes, barring a link to a verified site with logged session specs. See them as fun distractions, not facts. Outlets like the Daily Beast and The Guardian have covered 3I/Atlas, highlighting how tales split paths. The Daily Beast dove into extraterrestrial vibes, spotlighting Loeb's views and underscoring the oddities. The Guardian, drawing from established experts in its reports, countered that, backing the icy visitor idea and cautioning on hype. Both count as credible sources, yet they chase varied crowds and shape the tale accordingly. This isn't orchestrated deception. It's media adapting to reader tastes. The Daily Beast gets that its crowd craves the extraterrestrial what if. The Guardian's science beat caters to those seeking the expert's take vibe. Each side fuels the broader chat, though neither captures the full scene alone. Finally, the core query. If a team truly aimed to conceal a find, could they pull it off? Imagine JWST spotting clear artificial markers in 3I/Atlas's light profile. A sharp spike at a wavelength tied to our gadgets, but not cosmic norms, or heat outputs hinting at ongoing energy use. Might NASA quash it? In brief, nope, not indefinitely. The rationale? JWST readings flow via several channels. The Space Telescope Science Institute handles the crunching. Various collaborators on the scan request get eyes on it. Files get stored. Then after a private window, spill into the open. Reaching hundreds of researchers, everyone involved would have to be sworn to secrecy. But researchers aren't exactly known for holding their tongues, particularly when it comes to thrilling breakthroughs. The academic world thrives on breakthroughs, not hush-hush deals. Dropping a bombshell like, "We've spotted extraterrestrials," could land you a Nobel. Opting to lock that away indefinitely? You'd probably just get a quiet nod from some mysterious bureau that might not even be real. On top of that, 3i Atlas has been tracked by all sorts of unrelated outfits, far beyond NASA's gear. Think ESA's Mars probes, Earthbound scopes in places like Chile, Hawaii, Spain, and Arizona, plus hobbyists tinkering with setups in their yards. The Minor Planet Center has logged thousands of tracking reports from hundreds of sources. If NASA attempted to bury odd readings, another group would have caught it and gone public on their own. It's impossible to monitor every single viewing stream. Still, suppose hypothetically that the big players all teamed up to hide a find. That'd demand a plot stretching across borders, involving scores of groups and thousands of people. Schemes that massive crumble from the inside. Folks spill, leaks happen, or guilt forces someone to speak out. The grander the hidden truth, the quicker it unravels. Throw in a testable angle. Suppose a probe's flyby footage captured something jaw-dropping. How soon might it surface unofficially or get declassified? Drawing from past Mars mission schedules, initial findings usually drop in a matter of weeks. Complete archives follow in a few months. So if by late November or December we're still waiting on pics, it boils down to two options. The footage either isn't there, or it reveals nothing out of the ordinary. Either way, it undercuts the cover-up idea. Psychologically speaking, this wrap-up is key. Our minds are built to finish incomplete pictures. When details are missing, we invent scenarios to plug the holes, a leftover from evolution. Back in the wild, treating every bush's shake as a threat saved more lives than dismissing it as a breeze. Yet today, that instinct leaves us open to wild theories. Any info shortfall turns into a supposed smokescreen. Any holdup seems fishy. Any bland assurance like "no cause for alarm" comes off as precisely the dodge you'd expect if there were real issues. The fix comes in two parts. Start by grasping the bias so you spot it kicking in. Next time you're crafting a complex rationale for delayed releases, hit pause and consider if the plain truth is simply that analysis drags on. Then, insist on proof that matches the boldness of the assertion. Huge ideas, like global powers concealing alien evidence, demand rock-solid backing. A fuzzy snap and a gut feeling won't suffice. So what does this tangle of theories boil down to? The bulk stem from nothing solid. Plenty arise from mix-ups about how space operations run. A handful are outright inventions to drum up views or hawk products. But they stick around not because folks are dim, it's the messy info ecosystem. Official schedules crawl along, and the thrill of a mind-blowing reveal is flat-out appealing. We crave aliens out there. We yearn for a cosmos bursting with more than barren stones and clouds. That longing opens the door to stories dangling big on covers. Once the dust settles, once the Mars info gets crunched and shared, once closest approach is passed and fresh sightings roll in, most of these tales will slip away unnoticed. Fans will shift to the latest puzzle. Doubters will chime in with C. And experts will carry on as usual, gathering info, challenging ideas, tweaking theories. It's less flashy than a grand concealment, but that's the real path to knowledge. On that note, experts are still at odds over exactly what this object is. Time to dive into the strongest cases from each perspective. Part 13. Thinkers and experts weigh in. The research world isn't some uniform block. Step into a gathering of stargazers and probe them on 3i Atlas, and reactions will span from "clearly a comet, let's move along," to "we should hold off judging till the evidence seals it." Such debate isn't a flaw, it's science in action. Concepts clash. Proof settles the score. Let's outline the terrain. Kick off with the data-driven side. These are the pros echoing folks like David Jewett and Karen Meach, who've devoted years to probing icy wanderers and rocky bits, deeply familiar with what's out there naturally. Their stance is direct. Stick to the facts. Assume ordinary till shown different. They examine JWST's spectral data revealing water, CO2, CO, and carbonyl sulfide, all everyday icy compounds, and call it a comet. They see the lopsided haze and label it geysers, which is standard fare. They note the faint non-gravitational push regarding acceleration. Experts suggest it might stem from balanced jets or substantial mass, phenomena we've encountered in the past. For those adhering to empirical principles, the threshold for declaring an object artificial is exceptionally demanding, and that's entirely appropriate. History has tricked us before. When pulsars were first spotted in 1967, their rhythmic precision led Jocelyn Bell and Anthony Hewish to humorously label the signal LGM1, standing for Little Green Men. In reality, they proved to be spinning neutron stars, exotic yet entirely natural. The WOW signal from 1977 appeared as a focused emission from the cosmos, precisely the kind SETI sought. It went unexplained and never recurred, lingering as an intriguing puzzle without confirming anything definitive. Fast radio bursts puzzled researchers until we identified cosmic sources like magnetars and other bizarre entities. The recurring theme holds steady. An oddity catches our eye, theories proliferate, and eventually, conventional astrophysical accounts surface. The anomaly evolves into yet another natural phenomenon. Thus, empiricists advocate steering clear of that loop, exhaust every mundane possibility before positing advanced tech. With 3E Atlas, ordinary interpretations suffice admirably. Its composition stands out but makes sense chemically. Dimensions and weight remain estimates, yet they're feasible. The path traces a hyperbola, verifying an extrasolar provenance, without any evidence of artificial control. A comet profile aligns perfectly. Case closed. On the other side sits the pluralist or possibilist group, with a vibe emerging as the leading figure among several voices. Their stance offers more subtlety than media portrayals imply. They aren't asserting that 3E Atlas is unquestionably engineered. Instead, they contend that even if each irregularity can be addressed via natural processes, their collective buildup warrants responsibly exploring other options. Moreover, they highlight how the taboo surrounding talks of alien relics has led the field to undervalue such prospects. In a Vibe's perspective, his assessment framework serves as a resource director. A rating of 4 on a 10-point scale doesn't signal likely extraterrestrial. It indicates sufficient strangeness to justify ramping up scrutiny and observations to conclusively dismiss tech-based origins. It's essentially a prioritization mechanism. His core argument: if we perpetually overlook engineered markers assuming all is natural, we'll miss them entirely, should they exist. At stake philosophically is a deep issue. What qualifies as robust enough evidence for a bold assertion in astronomy? Insisting on ironclad certainty means rejecting every candidate, given the field's inherent ambiguities. We can't haul these bodies into labs or conduct precise tests. We deduce from spectral data, gravitational effects, and such, always with degrees of likelihood. So, the crux is, at what confidence level do we deem an alternative hypothesis worth pursuing? Typical scientists set the bar for artificiality sky-high, perhaps 99% or beyond. For a Vibe, it's more modest, around 60 to 70%. This reflects a core divergence in Pryor's and Bayesian reasoning. Both views carry merit. They're contrasting evaluations of risk. Empiricists aim to sidestep false alarms, shouting alien over mere space debris. Pluralists seek to evade oversights, brushing off a truly significant find because it defied norms. Shifting to institutional weariness, certain scholars react sharply to extraterrestrial queries, not from narrow thinking, but exhaustion. The topic has arisen repeatedly, yielding natural resolutions each time, rendering it a tiresome sidetrack. Anomalous comets, quirky asteroids, baffling emissions, all inevitably funnel through the aliens' grinder. Usually, the verdict is negative, yet the ensuing press frenzy and lay speculation generate clutter that impedes genuine inquiry. Observatories drown in proposal overloads. Inboxes overflow with media and enthusiast probes. Precious hours meant for breakthroughs vanish into outreach and rebuttals. This fosters a counterproductive dynamic. Public dives into the alien debate draw more spotlight, spawning further time sinks. Consequently, some experts opt out entirely. They tune out the hype and hone in on prosaic theories. Far from concealment, it's pragmatic scheduling. Still, this breeds an image of elite astronomers as aloof or inflexible, stoking the conspiratorial narratives we touched on previously. Lessons from history prove enlightening. Consider the Martian canals. During the late 19th and early 20th centuries, observers described straight-line formations on the red planet resembling man-made waterways. They were mere visual tricks and imaging flaws from coarse equipment. Pulsars, as noted, sparked fleeting notions of signaling devices. Closer to now, in 2020, the body tag 2220 CSO was first pegged as an asteroid, only later unmasked as a 1960s human launch stage. Detailed trajectory studies eventually exposed its man-made nature, but only after extensive review. Such precedents instill caution. Occasionally, the natural world throws curveballs that outstrip our wildest imaginings, turning what appears man-made into just another undiscovered earthly quirk. Yet every once in a while, though seldom, the bizarre turns out to be crafted by humans, much like what happened with 2020. Now, jumping from something human-created to alien origin is a massive stretch, but it's not entirely beyond logical bounds. Documented history shows it happening 0 times, which keeps the odds incredibly slim. Still, a null result from a limited dataset doesn't rule out future occurrences. It's smart to ponder the broader ramifications. Suppose 3I Atlas proved artificial, even if harmless. It'd spark debates on orbital regulations, airspace control, and engagement guidelines. The 1967 Outer Space Treaty oversees cosmic endeavors and views heavenly bodies as shared human treasure. However, it was drafted with only Earth-based players in mind. If an item gets verified as coming from beyond our planet and seems operational, who'd claim authority? Who calls the shots on outreach efforts? What dangers lurk in proactive signaling? SETI's post-detection guidelines urge global talks before replying to any intercepted transmission, but they're optional and proven and geared toward electromagnetic waves rather than tangible artifacts. If 3I Atlas was a scout craft actively gathering intel, do we reach out, flash lights at it, broadcast waves, or just watch silently to stay under the radar? These aren't lightweight issues. We lack unified resolutions. For sharing science with the masses, the key takeaway is balancing awe with restraint on absolutes. Folks merit straightforward facts. They need clarity on when a find is truly odd versus when it's amplified for views. Yet they also crave that thrill of exploration to join in unraveling the mystery. Striking that balance is tricky. Overplay the extraterrestrial angle, and you fuel wild theories. Underplay it, and you come off as dodging. The optimal path likely involves candor on ambiguities. This is our current knowledge base. These are the gaps. Here's our plan to fill them. Some experts back idea X, while others favor Y. Why the divide? Where's the expert consensus leaning now? Toward it being a carbon dioxide-laden visitor from interstellar space, though ready for plot twists. Stay vigilant in monitoring. Press on with scrutiny. Should a real oddity emerge, probe it thoroughly without biasing the outcome. Let the data steer the wrap-up, not preconceptions. Regarding the scoring controversy, the timeline speaks volumes. In early August, Low shared estimates across platforms that ended up cited as June 10th. Subsequently, via his Medium articles as JWST Insights rolled in, he adjusted to 4 out of 10. That's the mechanism functioning as intended. Ratings shift with fresh proof. As additional info arrives, particularly if 3-2 Atlas acts comet-like around perihelion, the rating ought to dip further. Anomalous actions could bump it up anew. The setup remains tentative, evolving, and evidence-led. Debating the exact figures matters less than embracing the idea that beliefs evolve with mounting data. Thus, thinkers in philosophy and physics deliver a divided verdict. The bulk sides with comet status. A few push for heightened alertness. Current proof backs the prevailing view, yet the possibility lingers open, and the impending Mars flyby could supply the clues to settle it. So what insights emerged from the Mars phase? Part 14. Outcomes from the Mars flyby. Okay, time to discuss our targets for this evening's Mars close-up and set realistic hopes. By the point this reaches you, 3I/Atlas has either zipped by Mars at its nearest or is mere hours away. The probe's tools are snapping readings or have just done so. But refined analyses? Those stay under wraps for at least days, possibly weeks. Hence, this bit serves as both recap and teaser for key things to once releases hit. Primarily, coma unevenness varying by sunlight position. Back in August, JWST spotted an off-kilter coma. That unevenness signals irregular venting. Specific streams push out material more intensely in certain ways. With 3I/Atlas progressing along its path and the Sun-Comet Observer alignment shifting, the coma's form should transform if sunlight drives it. Mars satellites, viewing from alternate vantage points unlike ground scopes, can verify if the unevenness aligns with forecasts. Matching thermal predictions would bolster natural comet traits. Mismatches, say, streams aimed unrelated to light, warrant deeper probes. Next, signs of focused jet streams or sudden bursts. Focused jets mean tight, directed ejections of vapor and particles, unlike scattered, wide dispersals. Columnar alignment offers clues regarding the makeup of the nucleus. Perhaps there are cracks or openings directing the material's movement. Outbursts represent abrupt, short-lived spikes in output. They might occur if underground reservoirs of unstable substances suddenly erupt to the surface. Such events are thoroughly recorded among comets in our solar system. Spotting them on 3 Atlas would bolster the idea that it's a comet. Not observing them isn't cause for panic, but it merits attention. Next, deviations in heat patterns compared to predictions. All celestial bodies give off heat radiation tied to their warmth. That warmth stems from sunlight absorption and how well they shed excess energy. On a comet, much of the heat output arises from dust particles in the surrounding haze, warmed by solar rays. Should infrared data align with anticipated dust heating at that solar distance, that's promising. But if there are unexplained warm or cool areas, that's noteworthy. They could stem from natural causes, like exposed icy patches next to dust-blanketed zones. Still, thorough simulations are essential. Once ESA or NASA shares initial results, key elements to scan in their reports include, first, their wording. Do they firmly label it a comet, or are they cautious? Terms such as in line with cometary processes or no irregularities found suggest routine findings. Wording like atypical traits or needs additional study could hint at curiosities. Second, details. Have they determined a spin cycle? Identified spectral signatures beyond JWST's detections? Noted shifts in output intensity? Third, analogies. Do they draw direct parallels between 3 Atlas and established comets, highlighting matches or stress distinctions? Align this against JWST's initial scans from August 6th. Has the CO2 to H2O proportion remained constant or altered? A move toward higher water content would back the idea of a radiative shell warming through, exposing deeper, water-laden strata that begin to release gases. Persistent CO2 dominance would align better with inherent oddities in its makeup. Was OCS, or carbonyl sulfide, still present? This delicate compound breaks apart readily under ultraviolet light. Its endurance would reveal details on the haze's protection or the core's release cycles. Does the limit on non-gravitational pull refine post-Mars flyby? Longer tracking periods and extended path data sharpen orbital calculations. Should the pull remain subtle, yet more reliably gauged, it favors a dense core scenario. If it ramps up abruptly or displays patterns clashing with simple outgassing, red flags emerge. Which theories hold up? Time for a candid tally. The comet theory gets a boost from consistent, organic patterns. If Mars observations reveal no shocks, if the haze develops as anticipated, and if the chemical makeup stays gas-heavy sans artificial markers, the comet view prevails. The alien object idea demands thruster actions or synthetic traces. Any spotted yet? From current path info, none. Should that persist via complete Mars data review, the odds of an artifact might fall from, say, 4 in 10 to just 1 or 2. Testing the wreckage cloud notion with one body is tougher. It would require spotting satellites or odd breakup signs, neither of which appears probable here. Flag any oddities. An atypical spread of dust particle sizes versus standard comets? Intriguing. Unforeseen glow lines or unforeseen compounds. Demand scrutiny. A flare in luminosity, an unexpected jump in bounced sunlight unrelated to familiar mechanisms that might signal an outburst or something odder. How info flows is key. How fast do groups release updates? Findings on a query site within weeks point to either simple analysis or urgency from surprises driving quick reports. Months-long waits are standard, though less thrilling. Keep an eye on symposiums. The American Astronomical Society runs sessions periodically. The European counterpart organizes events. The AAS's Planetary Sciences Division stands out as vital. When experts unveil 3 Atlas data at such gatherings pre-peer review, summaries and visuals often circulate openly. Separate hearsay from verified info. Vital point. If claims arise of ESA spotting a metal-like bounce, where's the proof? Absent from ESA's site, preprints, or multi-source validation, dismiss as speculation. Such talk could arise from mix-ups, intentional fakes, or early drafts adjusted later. Hold out for verified channels or vetted papers to endorse assertions. Cliffhanger choice, we must maintain intellectual integrity here. Suppose we spot an odd shimmer or a brief flash of light that lingers for seconds or minutes, something that doesn't align with standard heat signatures or spin patterns. What could that indicate? Begin by eliminating equipment glitches. Cosmic rays might generate fleeting bright spots. Stray sunlight or reflections off Mars could cause temporary flares. Next, dismiss ordinary causes. Particles of ice in the surrounding haze might reflect light sharply if aligned just right. Spinning debris could snag rays of sun at precise orientations. Finally, if those don't fit, explore engineered possibilities. A smooth mirroring panel turning into sightline would yield a foreseeable brightness pattern. Match the sighting against that forecast. If it aligns, it's deserving of closer scrutiny. If not, revert to natural origins. Validation demands repeated instances. A single sparkle piques interest. Several sparkles recurring at intervals synced to a spin cycle form a trend. Trends spark theories. Yet, truthfully, the probable result from this evening's Mars flyby is data reinforcing our prior hunches. 3I/Atlas is a substantial carbon dioxide-laden comet from outside our system. It's venting gases. It's atypical. It's ripe for study. But it's no alien craft. No piece of an apocalyptic swarm en route to us. It's simply the universe acting strangely. And that's the finest strangeness, as it opens doors to fresh insights on comet origins in distant stellar realms. More details will emerge in the weeks ahead, and the narrative will evolve. So what's on deck post tonight? Part 15. The prospects for the 4th interloper in our skies. Let's ground in certainties. 3I/Atlas hails from interstellar space. That's undisputed. Its hyperbolic path, speed, and measurements from numerous global sites all verify an origin outside the Sun's domain. It endangers Earth not at all. The nearest pass in December sits at roughly 270 million kilometers, over 600 times farther than the Moon's reach. Even under the gloomiest estimates of its scale and makeup, collision isn't in play. At perihelion, its sun closest point around October 30th, 2025, at about 1. For Australian dollars, lies our prime viewing slot, potentially resolving outstanding puzzles on its outbursts and makeup. Key insights so far. The prime revelation: interstellar bodies rich in CO2 do exist. Prior to 3I/Atlas, our lone interstellar comet was Borisov, water-dominated and resembling a local wanderer just visiting. Now, we recognize that extrasolar comets feature chemical mixes rare in our neighborhood's icy archives. That's unsurprising upon reflection. Varied stellar nurseries yield diverse setups, distinct disk heat levels, elemental mixes. A comet birthed near an M-type red dwarf would face unique heating patterns versus one around a G-type sun-like star. Variety is anticipated, yet witnessing it firsthand differs. 3I/Atlas supplies our inaugural solid evidence. Another takeaway: visible activity doesn't always mean hefty non-gravity thrust. The simple view holds that a visible haze implies robust speed-up from gas release. 3I/Atlas proves otherwise. Counteracting streams, hefty build, or their interplay can mute overall motion despite evident vigor. This influences simulations and path forecasts. Should upcoming scans spot dim, active extrasolar items, we can't presume major path shifts from venting. Precision tracking is essential. Looking ahead, The October 30th perihelion marks the highlight for watchers. Sun warmth maximizes then. Any surge in activity would hit peak there. Any change in CO2 to water proportions would show up around it. Ground observatories will monitor intently. Orbital scopes, if slots open, will join in. This represents our final prime shot to profile this guest ere it vanishes into obscurity. Elsewhere in space, alternative outposts beckon. NASA's Psyche probe, sent skyward in 2023 en route to the metal-rich asteroid Psyche, could snag views of 3I/Atlas from an offbeat solar vantage. ESA's JUICE craft, as noted before, might enable extended-range sightings along its Jupiter-bound path. These remain iffy. Primary missions take precedence, with interstellar guests as bonus aims, but a compelling rationale could secure slots. Prolonged trajectory tracking will refine as we follow 3I/Atlas sunward. Each extra month of data bolsters the path model, narrowing uncertainties in its course and sharpening our grasp of faint non-gravity influences. Forces. Should there be any concealed boosts or minor adjustments that existing observations can't clarify, ongoing monitoring will uncover them or verify they're absent. The Rubin era is on the horizon, set to transform the field entirely. The Vera C. Rubin Observatory, featuring its 8.4-meter mirror and vast sky coverage, will scan the whole observable universe multiple times, spotting fleeting and shifting entities much more effectively than today's setups. Projections indicate Rubin could spot one interstellar visitor annually, or possibly even more. Over the next 10 years, we might accumulate 30 to 50 verified ISOs. At that point, the numbers will start to tell a real story. We'll map out size ranges, material patterns, and speed directions. We'll determine whether 3I/Atlas stands alone or if CO2 heavy comets are typical. We'll figure out if massive items like this are odd exceptions or if our initial finds simply highlighted the luminous ones. Rubin will also pick up tinier bodies. Currently, our scans favor big or superactive ISOs since they're simpler to detect. Thanks to Rubin's precision, we'll begin noticing the little guys, the 100-meter rocks, the 10-meter fragments. If their size spread aligns with models for natural launches, that's reassuring. But if anomalies like odd clusters or voids pop up, we'll have fresh mysteries to solve. Let's evaluate how each theory holds up post-tonight and after perihelion. The comet idea boasts the strongest backing. Native gases? Yes. Uneven yet understandable haze? Yes. Subtle but present non-gravitational pull. It encourages bold individuals ready to suggest verifiable options, no matter how controversial. The method fixes mistakes, but only when someone has the courage or tenacity to put forward ideas that can be examined. Should 3I/Atlas prove to be beyond a mere comet? Should its closest solar approach expose some kind of adjustment? Or should extended observations detect irregularities? Then Lowe was wise to leave that possibility ajar. And the strict observers erred by shutting it too soon. Science progresses regardless, yet it thrives more when discussions remain straightforward and grounded in evidence. Envision the Martian sky at this very moment. Sparse air, reddish soil swirling below and overhead, detectable by devices if not unaided sight, an interstellar guest, a lump of frozen debris and stone, or perhaps an oddity, racing by at velocities that dwarf our quickest spacecraft, making them seem motionless. Orbiting sensors following its path, sending information homeward, where countless researchers and a vast public of inquisitive minds observe, speculate, and anticipate. Ancient key or false lead, icy body or engineered vessel, remnant of a vanished realm, or simply another pebble in the vast cosmos. The answer eludes us for now, but we're observing closely. We're quantifying. We're gaining insights. That's why this evening, on October 3rd, 2025, transcends a mere pass-by. It's an instant when humanity, bound to a single modest world, extends through its technology and calculations to connect with something born among the stars. The fourth interloper lurks out in the void, wandering through obscurity. We'll encounter it in time. It might turn out mundane. It might astonish. Either way, we'll be prepared, telescopes aligned, simulations honed, inquiries fine-tuned by lessons from the prior trio. The heavens aren't barren anymore. They're teeming with travelers. And we, brief guardians of this fragile azure sphere, are at last deciphering the clues. This night, we gaze upward. Come dawn, we anticipate. And amid the influx of readings from Mars, perhaps, just perhaps, the cosmos is whispering a secret.